Recording. Okay, today is June 26, 2023. Remember that I have recordings of this class of last year, right? In my YouTube channel. So if you want to review the report of last year too, yeah, you're welcome. But I'm still posting the meetings, the recorded meetings of the semester. Okay, as time goes by, I'm planning to do some. Thinking about doing some editing and compress the video only to a smaller amount of time, right? But let's talk about. Don't forget, the exam 2 is going to be this coming Thursday. The chapter is going to be 33 and 34. I put a little star here, so see notes for a specific, right? For specific sections of the chapter. Partial exams are from 12 noon to 2 p.m. and the final exam from 8 a.m. to 10 a.m., okay? That's what this start is all about. Let's take a look at the notes. The second exam is going to be a little bit less of material because we're now spending more time with the labs. Okay, so that was what we had for exam 1, right? Chapter 15, 16, all sections, and then those sections of 17, these sections of 33. Okay, and for exam 2, just the material that I covered up to Thursday last week. Whatever I covered today is going to be on the third exam. So 33.4, 0.5, 0.6, 0.7, let's take a look at the book. No, chapter 17. Yeah, I meant to cover those 2 chapters on 17, but we still didn't have time. I'll try to do that. If you have time before the end of the semester, I'll cover those 2. Those are 2 interesting chapters, very interesting chapters that you can understand with very simple illustrations, okay? Chapters 0.1, 33.1, 33.2, and 3 were for exams, for the exam 1. Exam 2 is going to be on polarization, reflection and refraction, total internal reflection, and polarization by reflection. Okay, and what else? Chapters 24, 34.1, images and plane mirrors, spherical mirrors, spherical refracting surfaces. Let's see. No, I skipped that, right? I skipped this one, and we went straight in 34.4 and 34.6. I want you to review that on your own. This one is a very interesting section too, but I'm skipping it, okay? So I'm not gonna ask that in the exam. But this one, there won't be any questions related to 34.6, but if you want to review how we found out those equations, right? That's where the section that's the section that has the proofs for the equations. So, okay, so here we go. So that's what we have. Exam, I'm gonna put it. All sections, right? Chapters. We leave this way, organized. Okay. And what we're going to do today is wave optics, by the way. And then we are going to continue with, after the lecture, we're going to continue with lab number 1. Wave optics is right in here. They don't call wave optics, they call it interference. But that's what we usually call wave optics, light as a wave, chapter 35. We're going to review Young's interference experiment. That's very important. You know, it's a historically important experiment. It's an experiment that we do today. Even today, we perform this experiment to explain the wave nature of light. And let's take, just from the historical point of view, let's see if they have it here. Young's double interference experiment. Okay. That's I'm going to elaborate. Let's take a look at Wikipedia so we can have a good historical background what how it works, right? So historically speaking, and before Young's experiment, light was thought to behave like a ray, light rays, okay? That's what Newton, that was the idea that Newton propagated. Newton and his contemporaries. But then later on, someone else called Young, let's go Young to Wikipedia to get a historical perspective. Double slit experiment by Young, right? Young's double slit experiment, Wikipedia. Right here. And Thomas Young, that was his name, 1801. Okay, that's so it was the 19th century. He came up with this idea. Let's take a look at he was born 1773, died in 1829, a British polymath. The individual was a polymath, individual whose knowledge spans a substantial number of subjects. Okay, so what we call today a Renaissance man, right? And who made notable contributions in the field of vision, light, solid mechanics, energy. We are specifically interested in his contribution for light. Language, polymath, language, musical harmony, and so on, right? Egyptology, wow, the guy was an Egyptologist too. He was instrumental. Oh, he was instrumental in deciphering the Egyptian hieroglyphs. Isn't that nice? In the Rosetta Stone. So that was critical, right? The discovery of the Rosetta Stone. But we are interested in his contributions to light, wave theory of light. That was his contribution that we are studying right now. Okay. The most important was to establish the wave theory of light, set out by Christian Huygens. Christian Huygens, who started that. To do so, he had to overcome the century-old view expressed in the venerable Newton's optics that light is a particle, that light behaves like a light ray, would travel only in straight lines. That's the important difference between light and wave, the particles and wave. Okay, nevertheless, in the 19th century, Young put forth a number of theoretical reasons supporting the wave theory of light. Okay, and he developed two enduring demonstrations. Look at Newton's contribution. Let's see where. Okay, Newton's contribution in optics was published in 1704. So we're talking about 100 years during which his ideas prevailed. But it didn't start with Young. Apparently, it started with Christian Huygens. Okay, Christian in his treatise of light. Okay, the nature of light propagation, right? Of course, light reflection and refraction. More students coming in. So going back here. 1704, let's it goes. Light was thought to behave like light rays or particles. Okay, particles only can travel only in a straight line from one point to another. The idea of waves were already around because the idea of waves, the genetic idea of waves, right? Not the specific idea of wave for light. The genetic idea of waves was already around. And people and scientists, right, could observe waves in a pound. For instance, scientists could observe waves in a pound and in strings. Right? However, there was no convincing evidence yet that light, by the way, under certain special circumstances, right? Very important, under special circumstances, would behave as a wave. Yes, light does have this particle behavior. Light, so much that we came up with the geometrical optics theory, right? To explain propagation of light particles. Then, I'm gonna put here, then the development of geometrical optics. Yes, but under certain special circumstances, light is going to behave like a wave, and that's what Thomas Young proposed and proved as well, and he provided evidence for that. Okay, as far back as 1604, no, 1704. Yeah, 1704 optics. 1704. The overwhelming evidence was for the particle nature of light. But starting in 1801, let's go back to Wikipedia. Theory of light. Views. Where did I see 1801? In his subsequent paper, let's see. Speaking on, okay. 1803. That's the description of his historic experiment. Where did I see 1801, right? But 1803, let's put 1803. Evidence 100 years later, right? Started to come about, started to appear, that light also would behave as a wave. 100 years difference. And, it's very difficult, okay, to introduce new ideas when you have this old idea ingrained in the scientific mind. It's an uphill battle. It's an uphill battle against your own colleagues, against your peers. So think about that. And that Most likely that's what Young had to face when he started advancing his new theory, his theory of light, of wave optics. Okay. The first thing that you have to know is we already introduced that to you. Okay. On wave optics is that the refractive index. Okay. We already know the idea of the refractive index, and we're going to work with this idea of refractive index throughout the wave treatment of light. Okay, the refractive index of light is the velocity of light in the refractive index of a material, not light, right? The refractive index of material is the velocity of light in vacuum divided by the velocity of light in the medium. And that can be expressed in terms of the wavelengths. Okay, that can be expressed in terms of the wavelengths and the period of the light wave. Okay, so here where we start to introduce the concept of waves. Okay, that's where we start. Here you can say it's just the concept of particles. The way that the concept of particles applied to light. But that's where we start to introduce the concept of waves for the light. You know, it's a wave that has a wavelength. It's a wave that has a period, right? And because the speed of a wave is the wavelength divided by the period, we can write something like that. Okay. And we can go ahead and here write that as lambda f in terms of the frequency, and lambda, the wavelength of the particle in the medium. Okay, that's what this lambda sub n is all about. The wavelength of the particle in the medium divided by the period of the particle in the medium. And I can here write that in terms of the frequency of the particle in the medium. But there is more to that. There is more to that. I'm going to write that down here for you. Note that the frequency of a given wave is dictated, must be dictated, right? Must be dictated not by the medium, the new medium, right, that the particle is propagating. So what's happening here? We have light, let's see here, I'm gonna get this. We have light here propagating from one medium to another, right? In this medium here, the light is propagating at the speed of the light in vacuum, which is 300,000 kilometers per second. And then when it encounters a second medium, it penetrates, and the light is refracted, right? So the question is, what happens to the wavelength of this particle when it enters the new medium? Does it change? Does it remain the same? What happens to the period of not of the particle, of the wave, right, when it enters the second medium? So that's what I am explaining there, right? So here let's say we have a wavelength and we have a period, but then if the speed of the wave is going to change in the second medium, there must be a change in one of those characteristics of the light. Is it just the wavelength? It's the period of the wave, or both of them? That's what the question is, okay? So consider, right? So what we have here, consider light propagating from one medium to another, right? The refractive thing, the refractive index of the medium is given by, right? And then I'm going to do, is given by that. Okay, if light can be modeled, okay, this is the very definition of refractive index in terms of the particle or light ray model. However, if light can be modeled as a wave, then the above equation becomes the speed of the light in vacuum, which is going to be the wavelengths lambda divided by the period, which, by the way, we covered in chapter 33, right? We just didn't cover the wavelengths and the period of the wave in a different medium, in a medium other than vacuum. And the speed of the wave in the second medium, that I'm going to call lambda n divided by Tn. What you have upstairs can be here written at lambda f. And what you have downstairs can be written at lambda n fn. We're going to keep it this way. We're going to keep this equation in terms of the frequency because it's more intuitive to understand, okay? So now you have to ask yourself, does the frequency depends on the characteristics of the medium or not, right? So you have to ask, yourself the following question. Does the frequency or period of the light depends on the characteristics of the medium? That's what you have to ask yourself. In order to answer this question, okay, in order to answer this question, you have to go back at how a given wave is generated, okay? You have to go back to that. So remember how a given wave is generated, even mechanical waves. You have to have a source of vibration. You have to have a source of vibration to generate the wave. And this source of vibration is going to generate a wave that's going to propagate from this point to another point. If light behaves like a wave, then the source of vibration of this wave, of this light wave, is going to be far away at the source where this light is being generated. For instance, at the surface of a star, for instance, right? So let's say they're at the surface of the star, or that at the, or even at the in the flame of a candle, you can model a light wave as being generated by some sort of vibration there at the source. That's very important. The source of vibration is at the source, okay? And that source of vibration that's far away here in this point is oscillating at a given frequency. If the frequency depending on the oscillation of the source that's far away from the second medium, it's very reasonable to assume that the frequency here of the wave inside this medium is not going to change. It's very reasonable to assume that the frequency inside this medium is going to be the same frequency as of that source that's far away in the first medium, okay? So that's the key point that you have to understand. And from this understanding, you can conclude that the frequency doesn't change. However, if the second medium has a different refractive index, then something else must change. And this something else must be the wavelength of the light, okay? And that's what I'm going to write that down here to answer, right? Oops. So the answer is here. Notice that the frequency of a given wave must be dictated not by the new medium, but by the source of the wave that is located far away from the new medium. Far away from the new medium. For this reason, right? For this reason, the frequency of the light wave cannot be different in the new medium. And the only thing that's going to change, the only thing that's going to change when a wave propagates, a light wave, right? A light wave propagates from one medium to another. Light wave propagates from one medium to another. From one medium to another will be the wavelengths. Will be its wavelength. So now we can go ahead and write the formula of the refractive index in a different way. So that's the conclusion that we have made. The conclusion that we have reached is this one right here. That the frequency of the light wave in the new medium is going to be equal to the frequency of the light wave in the older medium. Because the source of the light wave is in that other medium. Okay? The above must be true. The above must be true because the source of the light wave is in the first medium. And what's going to change? Well, the only thing that must change is going to be the wavelengths. Can you picture that? Think about that. Let it settle in your mind. And we can rewrite the new wavelength of the light as being the wavelength of the light in vacuum or air divided by the index of refraction. And that was exactly the illustration that I came up with, okay? Here you go, the wavelengths in air or vacuum. That's the distance between the wave fronts, right? The peak, the crest of the wave. When it enters the second medium, the wavelength shrinks, okay? As I told you before, for the sake of this course, n is going to be less than one, greater than one, because, you know, because n is greater than one, then the wavelengths of the light wave in the new medium is going to be shorter than the wavelength in vacuum. That's the important piece of information that you have to have. Okay. And I want you to have a very I want you to understand this notation here, right? What you see right here, this is a representation of a wave, a different representation of the wave. Each of those lines here means a peak, a crest, the crest of the wave. In between, right in the middle portion here, you're going to have the valley. I didn't illustrate the valleys here. And here at quarter of a distance, both here and here, 1/4 of the distance and 3/4 of the distance, you're going to have the nodes of the wave. I didn't illustrate nor the nodes, neither the valleys. Okay. And now I can illustrate my wave as being a planar wave. This is the illustration of a planar wave entering the second medium. It's very easy to memorize that. why light is bent towards the normal, not just in terms of Snell's law, but also in terms of analogies that we find in real life. Okay, here in this illustration you have the the wavelength of the light, right? Illustrate like a little blocks. But if you use this analogy of the car, a mechanical analogy of refraction, consider a car, right? Two wheels, 2 or 4 wheels, is a rigid body. So, the axle of the car represents the crest of the wave, and it's moving towards another medium, right? Here, let's say, here's the asphalt, and here's a grass surface. Why am I using this analogy? Okay, there's a reason why I'm using this analogy. In the asphalt, the car has more traction because the medium is more appropriate for the tires, right? Because the car has more traction, it's gonna drive faster here than in the grass. In the grass, you're gonna have less traction. Okay? So as the first wheel, and this car is coming at an angle here at the interface between the asphalt, which is one medium, and the grass surface, that is another medium. Don't forget, you have more traction here in the asphalt than in the grass. As this first wheel, this left wheel hits the grass surface, right? It's gonna lag behind this other one, is gonna slow down, right? This wheel is gonna move slower than this one. And this wheel here is gonna be move slower than this one. As a result, the car will tend to rotate from that original position to this other position. This wheel is going to slow down, this one is going to move faster. And this slowing down of this wheel will cause the axle to change direction, to change angle from one medium to another. Okay? Just like that. When the second wheel fully enters the grass surface, then both wheels will be at the same speed. Both wheels will have the same traction, and they will be moving at the same speed. Okay, so what causes the refraction of the light, or what causes the refraction of the wheel of the car, is the changing speed from one medium to another. Is the fact that one wheel is slowed down and the other is still moving faster than the first one. So you can think about that in these terms for waves. That's the analogy of refraction, okay? And because now the car is going to be moving slower, the wavelengths must shrink because the frequency cannot change. The frequency cannot change because it's what dictates the frequency is something else that is in the other medium. It's something that is in the other medium, oscillating in the other medium. Okay, so analogy, let's write down. Refraction occurs because of the analogy of the two-wheel vehicle, right? In other words, those wave fronts of the light that reach the slower medium, right? The slower medium, the medium with higher refractive index, okay, will move slower, whereas the other wave fronts will move faster and rotate the direction of propagation of the light towards the normal of the surface. That's another interpretation, another way of seeing the phenomenon of refraction. Okay. What else you have to know? Okay, so now you first thing, right? First thing, one, refractive index of a substance, of a medium, no, not a substance, but a medium, can be written down in terms of the wavelengths of the light. Okay, of the light. That's the important wavelength of the light in the medium, right? In both media, Okay. So that was the first way, that was the first hint, right? That light will behave like a wave. Okay, that was the first hint that light behave as a wave. Just by looking at the behavior of light when it refracts from one surface to another one. Okay, and then came the Young's experiment. Okay, on the double slit experiment, Young's double slit experiment. So let me walk you through how Young performed his double slit experiment. Okay, not this one. We're gonna go down here. Okay, here you go. Here's the double slit experiment. You have something that blocks the light, and then you have this passage, this little slit here and here. Okay. And today we can perform this experiment so easily, okay? Because today we have lasers, but Thomas Young didn't have lasers at that time. He had to go through great pains to simulate a monochromatic wave and also coherent wave. Today we don't have this trouble because we can buy lasers for $10 at any store, right? Even less. So here you go. These two slits are separated by a distance d, okay? And then we put the screen very far away. But very far away means, you know, put the screen far away from the slit at distance L, right? At distance L. Distance L, where L is much greater than D. That's what we mean by a very large distance. The distance must be much greater than the slit. And then, okay, here you go. I put here as well. And by much greater than D, it should be greater than 10 times D. And now we are going to come up with our wave, with our light wave. It doesn't have to be a light wave. It can be even water waves. Water waves under this condition is going to form interference pattern very far away. But That can be light as well. And that's what Young put himself to prove. Here's the representation of the light rays. Okay. And one light ray is going to pass through a slit. And let's say it's going to be incident in the screen at this spot. And the other light ray is going to be incident at the other spot. Okay. Like that. Make my slides look nicer. So it can give you the illusion of a movie, right? You know, one light ray, and then we have the second light ray. If light behaves as a wave, okay, then there must be interference between those two light rays at this point. Okay, there must be interference of those two light rays at this point. Here you go. Here's the illustration of my light wave, right? The distance here of this, the side here of this rectangle is the wavelength of the light. If there is a phase difference between those two light waves at this point, the point would be, okay, let's see here. Yeah, let's see here. Okay, well, let me move my screen because I'm not gonna want to go through the trouble of changing that, right? If there's a phase difference between this side here of the rectangle and the other side, then you're going to see an interference pattern throughout the whole screen. Remember, the interference is not occurring only here. The interference is occurring everywhere here in this screen, along this screen, okay? And how do we treat something like that mathematically? Okay, first we get the distance d2 that the first light ray moves, the distance d1 that the first light ray moves. Okay, but now remember one thing, remember something very important. This distance L is much greater than this distance between the slit D. So my drawing is not in scale, okay? Because the distance L is much greater than the distance between the slits, this angle that you see here is going to be approximately equal to this other angle here. Okay? That's what you have to believe, right? And this approximation is very important. And by the way, those two light rays, they're almost parallel because this distance is very far away. Because those two light rays are almost parallel, then the angle that this one makes with the horizontal is going to be approximately equal to the angle of this one. Okay, and by the way, is going to be approximately equal to this angle here. Okay. So the best way of putting this slide together is like that, showing oops, that would be the first one to be shown, right? I want to try to get this thing there. Let's see. This one. I'm going to do this way, in the following way. Oops. Leave it for future reference. This one here. We take the angle theta with respect to the midpoint. That's what I'm doing here. I'm taking the angle theta with respect to the midpoint of the two slits. Right? Instead of using this one, I'm going to use this one here. Let me get this guy right in here. make it black. Okay, I'm going to eliminate this one here for now. And then I'm going to get it back. This one I'll keep this one for now. Oh, yeah. Yeah, okay, I'll take it out. That's midpoint. I'll take this one out too. Okay. And then we have my first light ray in the figure, in this figure here. And I'm going to have my second light ray in the other figure. Middle, first light ray, second light ray. Okay. If this angle is equal to theta, right? If this angle here is equal to theta, then the other two angles must be approximately theta as well. That's the important approximation that you're making here. Those two light rays are going to be almost parallel, and consequently, they're going to be also almost parallel to this other middle light ray. The difference is going to be so small that we can neglect it. And now I can delete those. Light rays. Okay, let's do that again. Here you go. Middle line going to the point where the two light rays are interfering. First light ray at that point of interference, second light ray at that point of interference. The distance is D2 and D1. Okay, and all those two angles are going to be approximately theta because the path of the rays are going to be almost parallel. And why they're almost parallel? Because L is much greater than the distance D. Distance D is something like that. Okay. And then what's next? Okay, because those two light rays are almost parallel, we can go ahead and project a right angle triangle here. Also, because those light rays are almost parallel, this distance from here to here is going to be D2, approximately D2. And there will be a path length difference equal to that. Why am I doing this path length difference? Right? Because I want to find the phase difference between the light rays. Here you go. The distance from here to here, okay, should be a little bit here. Right? Here you go. It's going to be approximately D2. And we are left with this difference in path lengths. One path length, a second path length. And here is a difference in path length. This difference in path length used to result in a difference in phase of the two waves. Okay, and then we can construct a right angle triangle. That's what I did here. D1 minus D2. And then you have to believe that this angle is a theta angle. Okay. Why is a theta angle? Remember, this is a theta. This is theta. This is 90, right? This is going to be 90 as well. Approximately 90, right? So here is 90. Definitely here is 90, right? 90 degrees. If this one is approximately 90, this angle here must be theta, right? It's just a matter of rotating this this angle right here, this triangle, right? This side of the triangle. And now that we found out the approximate angle of this triangle, right angle triangle, what can we do? Okay, we can come up with an equation of the path length difference in terms of the distance between the slits and the angle that's being projected far away there in the screen. Okay. So I'm going to write down here, d1 minus d2 divided by d is sine of theta. Okay. So let's write it down in this one. Looking at the two-slit experiment illustrations, we have the following. One, two slits separated by a distance d. Two, one light ray propagating from one slit to a far away screen. Okay. The distance, two slits separated by distance d. Let's put it here like that. A far away screen, located at a distance L from the slit, from the two slits, okay? L much greater than D. One light ray propagating from one slit to a point in the screen, to a point on the screen, right? On the screen. A second light ray propagating from the second slit, to the same point, right? To the same point on the screen. Okay, because L is much greater than D, these two light rays are almost parallel to each other. Almost parallel to each other. Consequently, their angle with respect to the horizontal are almost the same. Okay. The path length difference is d1 minus d2, right? Second light ray propagates from the second to the same point. Let's say one light ray propagates from one slit to a point in the screen, a distance d1. Okay. A second light ray propagates from the second slit to the same point on the screen at distance d2. because L is much greater than D. These two light rays are almost parallel to each other. Consequently, their angles with respect to the horizontal are almost the same. The path length difference, yeah, I put D1, right? D1 minus D2, but that's okay. It's not a very fortunate notation, but just remember, is the distance that each path ray travels from the slit to the screen. The path length difference is D1 minus D2. This difference can be approximated as let's see here, this one here. That's the approximation. Going back to the drawing, right? So I extracted this right angle triangle from here. If you want, you can do the exact solution. Okay, if you want, you can do it. But it will be very involved mathematically. So that's why we do this approximation. D1 minus D2 divided by D is approximately sine of theta. Okay. So we can here write this equation, right? As this sine of theta. Oh, this sine of theta. That's the path length difference. Okay. Now let's look closely at this path length difference, right? If the path length difference is equal to integer wavelengths, we have constructive interference, right? Make sense? So it's like that. If, no? I'm going to write like this way. If D1 minus D2 is equal, I'm not going to be approximately, but it's going to be equal to one wavelength, two wavelengths, three wavelengths, and so on. Oops. Whereas n is an integer, right? Whereas n is where n is an integer, we have constructive interference. On the other hand, we have constructive interference at the screen. On the other hand, and if D1 minus D2 is equal to, let's say, half of a wavelength, no, 3/2 of a wavelength, 5/2 of a wavelength, and then we can write that down as B. To n plus 1. I'm going to erase that n, half of a wavelength. Where n again is an integer, we have destructive interference. We're going to finish right now so you can go in our break. Okay, but let's not forget D1 minus D2 is approximately equal to this sine of theta, right? Where theta is that angle that's formed by this line with the horizontal direction. That's So let's not. Now I can put approximate sign here. If in lambda in other words, using using the above approximation. We do this approximation because it's very convenient, okay? Using the above approximation, we have if, then we have constructive interference on the other hand, right? On the other hand, if the sine of theta is approximately that, we have destructive interference. Constructive interference, destructive interference. Okay? So that's the theory behind the two-slit experiment. We're going to elaborate a little bit more. Before we go, let's see if I can get you some illustration. We do this experiment, by the way, at LA Harbor. We have slits in there, and we can perform the two-slit experiment with a laser, and we do see a clear interference pattern on the screen. And I want to show that to you. Interference, two-slit interference fringes, two-slit interference fringes. See here. I want to see actual images. Let's see. Oh yeah, right in here is an actual picture. Okay. It looks just like that. Oops. Okay, it looks just like that. So that's what Thomas Young got at that time. Particles are not supposed, if light is a particle, it was not supposed to display this type of behavior when you project it over a faraway screen. So the moment that he saw this pattern in a screen, he proved to his peers that light behaves as a wave. Here we have constructive interference, constructive interference, constructive interference. Here, the black spots, we have destructive interference, destructive interference, destructive interference. And by the way, don't forget, this is the intensity pattern, okay? It's the square of the wave. The square of the wave. There's no negative intensity. Negative intensity doesn't exist, okay? So what our human eyes perceived is not the amplitude of the wave. It's not the positive and negative amplitude of the wave. That's not what our human eyes perceive. What our human eyes perceive is the amplitude of the wave is squared. Is the square of the amplitude of the wave. Okay? So that's why we have this bright spot here and this dark spot here, which corresponds, by the way, corresponds to the valleys of the waves, of the interfered waves, okay? And we can derive that nicely, but before we go through that, Sydney, are you there? You want to take attendance and we're going to go for our break.
Yes, I'm here.
Thank you, Sydney. Amy, are you there? Let's see. Oh, okay, good. So Amy is there. Okay, Andy. I don't see Andy here. Alex Hernandez. I don't see Alex either. Huh? Sartak. Okay, thank you. Basilio,
Here, Professor.
thank you. Jeshwan,
I'm here, Professor.
thank you. Zaid. Okay, Zaid is here, right? Okay, thank you. Sumana. I can see Sumana here. Okay, good. Thank you, Sumana. Alisa.
Here.
Okay, I heard Alisa. Thank you. And Kartika.
Here.
Thank you. Mary.
Here.
Thank you, Mary. Raymond. Thank you. Ashley, Ty. Hi, Ashley. I see Ashley here in the list. I don't hear from her. I want to put a star here. Kirakus. Kirakus earlier, but I don't see him. Okay. Alexis Valley.
Here.
Thank you.
Thank you,
Yes.
beautiful.
Okay. We have 12, 13. Okay, good. The numbers match, and it is 9:11. So we're gonna go AM to break, right? Break from to 9:26 AM. Okay. So I see you shortly. Ashley, okay, let's see. Okay, Ashley Ty. Anybody else? No, that's it, right? I see you in 15 minutes. Okay, so we are back here, and there is one student who came in, right? Let's see who is that. Is that Alex? Alex, are you there? Okay, Alex Hernandez, right? Okay, good. Thank you, Alex. 14. So let's continue with that theory. Okay, going back to that interference pattern that we do observe when we have something like that, a true slit experiment, and this distance must be very small, okay? For this interference pattern, for you to observe this interference pattern, the distance between those two slits must be very small, on the order of the wavelengths. If the distance is not very small, the distance is large, you are not going to see a pattern like that. Oh, for you to see, for you to see an interference pattern, and I'm going to get that from Wikipedia, by the way. Let me copy this image. No, let's see here. Save image. I gotta download this. Download it. Interference pattern. Double slit experiment with a monochromatic light. That will be a green laser. For to see an interference, the distance between the slits must be very small. On the order of a wavelength. Now let's proceed with this theory. Okay, now we found when do we get constructive and destructive interference, right? I will put this one here. And we can now and by the way, a full wavelength means, let's see, let me write down something again, something else here. Okay. By the way, a full wavelength means a 0, 360, 720, even better. I'm gonna put 2 pi, okay, 2 pi. Better do like that. 360, 720, and 360 degrees, okay? In phase difference. Phase is just that thing that goes inside the cosine of the wave, okay? N times 360. And full wavelength. When the phase difference is equal to that, we have a constructive interference of the wave. Now, let's write down those equations in a different way, okay? So we go for constructive interference. We have, and by the way, I'm going to rename this theta because it's constructive interference. That's going to be the angle theta in which you're going to see a bright feature, in the pattern. Okay, and we can find out what this angle is going to be just by taking the arc sine of whatever is in the right side. Arc sine. Okay. The first solution that we see here, the first solution we see from, the first and easiest, right? The first and easiest solution we see from this equation equation is for n equal to 0. Okay. For n equal to 0, or your theta bright is going to be what? 0 degrees, right? Cosine of 0 here is going to be 0 as well. That's the first interference. That's the first bright spot that you're going to see. Going back to my interference pattern. How do I? Okay. The bright spot would be the one that's right in the middle, somewhere around here. 1, 2, 3. 1, 2, 3. Yeah. The theta equal to 0 degrees will be this one right in here. See, 1, 2, 3, 1, 2, 3. And in my drawing, the bright spot will be exactly this one right in here. At the middle of the screen, okay, in between the two slits. And then you're going to have right fringes spaced, kind of evenly spaced. Okay. And we can even make an approximation, by the way. We can even make a second approximation for the small angles, right? We also have a second approximation. And by small angles, we mean, all depends on how picky you are, right? For small angles, we have this approximation. And now, for within the small angle approximation, you can see that the bright fringes are evenly spaced by this difference here, lambda over d. And let's take a look at our, it looks like they're sort of evenly spaced, right? You can come up with a ruler here and measure the distance between each consecutive bright spots. But that's only for small angles difference. Small angle difference. As the angle becomes larger and larger, more than 10 degrees, right? Then it's not going to be that evenly spaced anymore. What about for destructive interference? Let's go to, and just go copy and paste here. For destructive interference, we have 2n plus 1 divided by 2, right? Like that. We can even come up with a slightly different equation, but it's the same. It's going to be n plus half. And I'm going to put the parentheses here. And that's no longer an approximation. This one is going to be an equality. This is an equality, right? But this here is an approximation. And just like before, we are going to have n plus half lambda. Oh, it's not going to be bright, it's going to be dark. It's not going to be dark, it's going to be dark. Dark. And lambda over d. Here is going to be, what will be the very first one will be to do like that for n equal to 0. Here is not as straightforward as the other, right? Not as straightforward as the other. Because the wavelength and the distance between. Oh, it's going to be dark. And you can come up with an approximation again. Dark here. That's going to be this one. Let's do that for n equal to 0. For n equal to 0, what do you get? We get this one. I'm gonna put comma 0. 2D. Okay, for n equal to 1. For n equal to 1, what we're gonna have? We're gonna have 3 and 3/2. Right? And by the way, it should be any integer, can be negative numbers as well. For n equal to 2, it's gonna be 5/2. N equal to 2. Right? And you can see that there is a pattern, delta theta between one and the other, you know. Theta 1 minus theta 0 is going to be 3 lambda over 2d. Okay. Is going to be 2 lambda over d, right? Which is going to be, here's an equality, lambda over d. They were going to be equally, almost equally spaced. If we use the genetic equation, right? The genetic equation, n, that would be comma n. And then we go ahead and do the difference between dark n and dark n minus 1. Oh, sorry, let's put, yeah, we can do this way. No problem. Go. And here, n minus 1 is going to be here. We put everything under the same denominator. Here's going to be an equality. This n cancel out with this n. This half cancel out with this half n. Right? And we have minus, you know, we have 2 lambda, right? Minus is plus, and that was plus, and we have 2 lambda over d. 2 lambda over d. So for small angles, the spacings are even as well. Important characteristic of those dark spots. How small must be the angle to? Okay, the small angle approximation. I remember I did that before, right at the beginning of the course. What people usually tell Raymond is what they usually tell us in undergraduate school is that small angle approximation means less than 10 degrees. Okay, but let's see if I have it, the approximation here that I did before. let's see, maybe it's here. But if you're not that picky, you can go all the way up to 40 degrees, okay? I don't have it here. I must have done it somehow right here. Here's the small angle approximation, okay? Here you go. Here's the, don't forget, the small angle approximations. When we're talking about the small angle approximations, you got to consider that the angle is measured in radians, not in degrees, okay? Make sense? Take a look here. I have the sine of theta, I have the theta, I have the theta in degrees, theta in radians, and sine of theta. And what I have here is the percentage difference, okay? When the angle is 0 degrees or 0 radians, sine of theta is equal to theta, right? Because 0 radians and sine of 0 degrees is going to be 0, so the percentage difference is 0. Okay, but then when you start increasing the angle, the value of the angle, here is 1 degree. Here's the theta in radians of 1 degree. And here's the sine of theta for 1 degree. See the percentage difference? 0.005%. They're almost the same. But as the angle keep on increasing, you know, we start to get some difference. At 10 degrees, notice the difference here. At 10 degrees, the percentage difference is still very small. It's 0.5%. Okay? It's 0.5%. That's what they tell us in undergraduate school. That's what they tell us in high school, that the angle must be less than 10 degrees. Actually, you can go even further than that, because especially if you're not picky, let's say if you can afford a 10% difference between sine of theta and theta radian, okay, you can go all the way up to 44 degrees. See that? Okay. So it all depends how picky you are, okay? For my classes, you know, if you're an undergraduate student, you know, I like to tell my undergraduate student, okay, if you're an undergraduate student, you're okay to be within 10% difference, right? Now, if you're a university professor, you're okay to be within 5%, okay? Now, if you are a multinational company, like Texas Instruments or Apple, right? It's not okay to be within 5% difference. It's not okay. Their standards must be much higher because they're mass producing devices. A Boeing, for instance, a Boeing cannot have a percentage difference between their theory and real life of 5%. Because if they have a percentage difference of 5% in their airplanes, 5% of their airplanes would be crashing. And you're going to have a huge bill to pay to your customers, right? So a company like Boeing, Texas Instruments, you know, they're, oh yeah, the Titanic submarine. Oh yeah, do you see what happened to that guy, right? You see what happened to that guy, right? The millionaire guy that want to, yeah, they were crushed, right? And there were people that they were sounding the alarms, and the millionaire didn't bother. And they were crushed and just disappeared. You know, they cannot get their remains, right? So that's you know, when you're talking about the percentage, when you're talking about up to which angle, right? It all depends how picky you are, how picky you must be, right? It's not just how picky you are, but how picky you must be. For the sake of most courses, they say 10 degrees. But keep in mind that if you're not that picky, if you want a 5% difference, you can go all the way up to 31 degrees. And if you think you can go all the way up to 10 degrees without losing any customers, right? You can go all the way up to 43 degrees. In my exams, you know, I consider 5% a difference between whatever you get in the exam and whatever is the actual result, okay? So that's what small angles mean. And here you go. That's the difference between each dark spot. And I have an illustration of the fringes in my notes, right? Here's a bright spot. Here's a dark spot. Interference pattern produced by 2 slits. It's something like that. And you saw the picture as well, the actual picture, real life picture. in my illustration, I put the dark fringes a little bit more thicker, right? And well, we can do something else. We can do something else, okay? People usually do that. Going back here to my drawing, let's locate the dark spots in terms of the position Y, in the Y direction. People do that as well. Let's see if I have it here. No, I don't have it. Okay, but the Y-axis is this one here, in the vertical direction. And by the way, this is the dark spot, not the dark spot. This is the bright spot, right? The spot is bright because the pass length of this light ray is exactly equal to the pass length of this light ray. You make equilateral, not equilateral, isosceles triangle, right? This side is equal to this side. That's why you end up with a bright spot. Now, if we now consider this axis here being okay, the y-axis, we can come up okay with an equation in a different way. And by the way, I'm going to do this one here. It's better, this one. Oh, here you go. Oh, I already have this one. Here you go, y-axis. Okay. Y here is going to be what? Y divided by L is tangent of theta, right? So there's another way of locating the bright and the dark spots. Here we locate the dark and bright spots in terms of the angle theta. What if we locate the bright and dark spots in terms of the y coordinate, L tangent of theta? Okay. So y bright, theta bright. Y dark, theta tangent of theta dark. Okay. And now we're going to do an example. So you can have a numeric idea. Example, two slits separated by 0.03 millimeters. That's how good they can make those slits separation, which by the way is equal to 30 microns. Okay. 1, 2, 3. 1, 2, 3. L is 4.8 meters. First dark spot is 4.5 centimeters from central maximum. Okay. There's a simple experiment that you can make to find the wavelengths. Find the wavelengths of the source. What you see here looks like something that out of this universe, but no, it's an example of real life. Okay, two slits separated by 30 microns. The distance to the screen is 4.8 meters, and then you go ahead, get a ruler, right? Get a ruler, measure the separation between the first bright spot and the first dark spot. That's what the experiment is all about. from the central maximum, okay? Find the wavelength of the source. Solution, right? So we go ahead and, because it's a, you can even use either use the kind of exact solution without the without the second approximation, right? You can use this one here. Let's use this one here first. Here you go. Two slits separated by point. Central maximum is the first dark spot. So the first dark spot is located at n equal to 0, right? First dark spot is located at n equal to 0. To the, like that. We don't have the angle, but we have the distance from the central maximum. Okay. I'm gonna put it here. That's the distance from the central maximum, right here. And the first central maximum is located at 4.5 centimeters. The distance L is 4.8 meters. 8 meters. And then we can find out what is the tangent of theta dark, right? So we go equal 4.5 centimeter divided by 4.8 meters. Right now, this is not an approximation. This is not an approximation yet. But now we are going to make an approximation. And the approximation that you're going to make is another approximation that you know for small angles. Okay, not only sine of theta is approximately theta, but it's also approximately tangent. Okay, let's compare here with my, okay, I'm gonna put tangent of theta here. And then I'm gonna put the percentage difference again. Tangent of theta is tangent of 0 radian equal compare that here, right? 2419, okay. The difference starts to happen, you know, in the third decimal place. The third decimal place is less than 1%. Okay, so now let's calculate the percentage difference between one and the other. Let's see, can I do that? Yeah, the percentage difference is going to be, no, this one here. This one right here. E3. Yeah. Okay. 0.015%. Let's see when we start to get a 10% difference. 10% difference is 27. Okay. So the second approximation is not as good as the first approximation. Okay. Okay. That's the first approximation, right? And that's the second approximation. Note see that the second approximation is not as good as the first approximation. You start to diverge a little much earlier. Less than 5%, would be, for tangent of theta, would be around 18 degrees. Okay, so this approximation works for angles less than 18 degrees. And now we use the other approximation here. We have this relation here. D is what? D is 0.03 millimeters. I didn't use D yet. I used Y, I used L, and now I must use, oh, don't forget to multiply. Otherwise, I'm going to think it's 20.03, right? Let me put the multiplication sign here. There you go. And then we can solve for lambda, provided, of course, I change the units. Okay. Lambda. And you do the math. I'm not going to do the math. Okay, you can do that yourself. I'm just going to show you the final answer. What I am getting here is 563 nanometers. And don't forget, it's an approximation, right? But it's a very good approximation, 563 nanometers. 563 nanometers is which color? It must be the green color, right? Let's take a look. This one, let's say green laser. Well, green color wavelengths range. No. Green color wavelengths. Wavelengths range. No, it's a little bit, okay, green, yeah. See that 500 to 570 nanometers. We're getting 563. So this experimental result correspond to green color. So that's one way of determining the wavelengths of light by doing the simple double slit experiment. And now we are going to calculate the intensity distribution of the interference pattern using this theory. Intensity distribution of the interference pattern. We are going to use the same, and by the way, that's going to be an approximate solution. I'm going to tell you later on why it's an approximate. And that I'm going to give you a hint right now why it's an approximate solution. Okay, that's real life, right? And okay, right in here. Yeah, that's real life. The spots, the bright spot keep on decreasing, just like you saw in the other one. And what we're going to do, you know, intense distribution of the interference pattern. Approximate solution, and there is you're going to understand why is an approximate solution very soon. Find the intensity distribution of the interference pattern using the theory, the wave theory we covered before. Okay. Just recall, since we have two light rays, you know, the first light ray can be described by a wave, by the following wave, this wave here. kx minus vt, right? And then the second wave, the first light ray, something like that. And the second light ray is going to be something like that as well, okay? So when you look at this light rays propagate from one point to another, you have to visualize that sine wave waving its ways through that point there in the screen, not only for this one, but for this one as well. At this very point, this single wave that propagates from here to here is going to interfere with this other wave right here. That's how you should visualize it. And this thing is not static, it's actually moving, right? That's why I have the VT here. And I have my phase angle right here. My phase angle, which I told you is related to the path length difference. Okay? What we're going to do, first step, solution, right? Solution. Find the intense distribution of the interference pattern of a two-slit experiment using the wave theory we covered before, right? Consider for a known wavelength at a given position x. Position x. Like that. Going back here to the drawing, right? Here's the x-axis. Oh, actually, it's going to be the x like that. That would be the x. This one has one x, this one have another x. Solution. Each light ray, right? And let me put that between quotes, each light ray can be described as the following wave. It's an electric field. And by the way, it's an approximation because I'm saying the wave is a planar wave. You know, strictly speaking, it's not a planar wave. Strictly speaking, the intensity of the light wave is decreasing, okay? Strictly speaking, the intensity of the light wave is decreasing. That's why I put this approximated sign. But let's go ahead and okay, at the same position. Let's see here. Okay. So at that position, let's see here, like the two waves are interfering there, right? So the net wave will be okay. Now one more thing here, position. What we have to do now, okay? Consider that x is equal to 0 at the point of interference. Okay, so it is along the x-axis. So in this case, what we end up having, now I'm going to put the equal sign here just to simplify. Here is going to be 0. Here is going to be 0, right? Minus kVt. Minus kVt. Minus here. And something like that happens to this one, right? minus KVT. What matters is the phase difference at that point. It's not the position at all, okay? Minus KVT, right? Plus phi. And I erase that one here. And I can go the next step and say that this wave has a minus sign here, right? And we invert the signs of the argument. And now we can write down the net wave. The net wave, or the interference of the two waves, is going to be given by E1 plus E2. Okay? We don't want to keep this X around because this X is the position where the waves are located. Is the position where this X is not varying. The only thing that's varying is the electric field of the wave as time goes by, right? The screen position is not varying back and forth. No, the screen position is fixed in there. That's why you can eliminate the X from the argument there. And E1, that's E1 here. That's E2. Okay. And now we are going to put a parenthesis here. And this is a type of problem that we saw before. You know, how to sum up signs of two different arguments. Okay, we saw that before. And get something that is easier to visualize. Okay, and it goes like that. I'm gonna rewrite it here for you. Sine of A, sine of A plus sine of B. A is here, B is here. It's gonna be, just refresh your memory, sine A plus B divided by 2 cosine A minus B divided by 2. A plus B divided by 2. Cosine A minus B divided by 2. And then we can go ahead, replace that here. We just do this transformation so you can have a better idea, has a better visualization in the equation, right? Here you go, A plus B. A plus B. A minus B. And then can you go another step? Because this one becomes 2 KVT. minus the phi angle. And by the way, I'm going to, and this one disappeared. You see the temporal dependence on the second term here of the multiplication disappeared. What I'm going to do, I'm going to invert the order of the terms. We still have a temporal term here. KVT pi over 2. And now you can see that you have this term here that is, let's see this negative sign here. Yeah, we can keep this negative. Notice that now, and by the way, okay, yeah, okay, we can keep this way. Notice that we have here a phase term that's gonna vary, right, from 0 to 360 degrees. And now this is not intensity yet. This is just the wave. Okay. And one more thing, very important here, 2 pi over lambda. Remember KVT, right? What's KVT? KVT is 2 pi over lambda. Pi over lambda. V is going to be lambda F. Lambda cancels out with lambda. Oh, not this one, yeah. I'll switch their positions. Oh, this one here. This one goes to the other side, right? Now note CKVT is a function only of the frequency. Okay? And then be reminded of the frequency of the light. When we saw before. Be reminded of the frequency of the light. Let's take a look. Going back here to our in chapter 33. Okay, electromagnetic waves, right in here. My book doesn't work, so let's go there to the internet. Frequency of electromagnetic waves, even of the light. Look at the frequency of the light. It's very high. Terahertz. Okay, it's not megahertz, it's not gigahertz, it's terahertz. It's so fast that the eye cannot pick up the oscillation of the wave as it changes, right, position. Okay, so be reminded the frequency of the light is very high. It's very high, on the order of terahertz. Okay, the oscillation is so fast that our eyes cannot pick up any difference. As the wave oscillates. Consequently, we see an averaged value. So when we are performing those experiments, like the one you saw, here you go. Strictly speaking, you know, when you are performing this experiment, this intensity is oscillating very fast. It's so fast that we cannot pick up this oscillation with the eye. For this reason, we see a steady image, just like we see right in here in this picture. Okay. Not only that, average value, not only that, but the eye cannot see the electric field. Instead, cannot see the electric field amplitude, right? Amplitude. Instead, it sees an intensity which is proportional to the square of the resulting E field. Okay, so let's go here. The intensity. And by the way, I'm gonna put point P. Point P is going to be not gonna be equal, but it's gonna be proportional. You know, proportional to the square of this intensity. When we square that becomes 4 here, right? E naught square, the cosine square, and this sine square, which by the way is changing as time goes by, right? That's at a given instant t, and I'm going to emphasize that this intensity is at instant t. But like I mentioned, this variation is so fast that the eye cannot pick up the change in intensity as time goes by. So what we end up picking up is an average value, which, by the way, is equal this. The average of that is going to be average. We're going to do it in a different way. Here you go. T average is going to be proportional to the average of this term that, by the way, ends up being the average of the sine of square is going to be equal to half. How do we find that? You know, I'm going to just give you the integral, and then you can do that. We average over the period of the wave, okay? And in order to average a continuous function, we don't do a summation, we do an integration. Okay, and the integration is going to be given by 0 to t like that. When you take this integral, it's possible to solve this integral. I'm going to tell you. This integral is equal to half, okay? I have that spelled out in my notes. And not half, but t over half. T over 2, half of t. Let's see. Oh, wait a minute. This integral is t over 2. But don't forget that we still have the 1 over t, like that. Okay, and then it's not difficult to memorize that the square of a function, of a trigonometric function over its period is going to be half. And then finally, you get okay, we get, substitute that by half. And then proportionality here. If you're going to put it at equality, we can replace these two E naught by a maximum intensity. Oh, maximum intensity here, like that. Don't forget, this guy here is what? This guy here is the phase between the two waves. The phase between the two waves, is proportional to the path length difference. Okay. And the path length difference we calculated before, d1 minus d2, right? Let's go ahead. I'm going to even put delta d now. Going back here. D sine of theta, right here. Okay, here we go. d1 minus d2 is like that. And there is a relationship between the phase difference and this path difference. Okay, I told you before that a full wavelength corresponds to 360 degrees or 2 pi radians. Pi radians, okay? So all you have to do here is to do a simple calculation, okay? We can, rule of 3, right? We can come up and say, look, d1 minus d2 is our phi path length difference. I still didn't use the approximation, okay? This is the approximation. But we also know, right? If we divide that by the wavelengths, that these wavelengths correspond to a phase difference equal to 2 pi. 2 pi. Like that. A simple rule of 3. Okay, now I'm gonna use the approximation. Okay, and here you go. Approximation right in here. Very soon we're gonna go in a break, right? Who's coming here? Kartika? Okay, that's d1, d sine of theta is gonna be divided by lambda. Right? Here you go. This guy is approximately equal to this guy. And we have the following relation for the phase difference. I'm gonna even put the lambda downstairs here, so I can put this guy, this d sine of theta separately, like that. Didn't work, huh? Let's do that again. Lambda, yeah, now we have it. Here's my phi, and I don't need that anymore. 2 pi d sine of theta over lambda. And finally, we can plug this guy here in my equation for the intensity. Okay, let's not forget that's going to be an approximation, but it's still a very good approximation. This phi go inside of here. We can come up with another step here. These two cancel out with this 2. Lambda. We have a pi upstairs. Pi d sine of theta over lambda. And now we're going to plot. It's not easy. It's not something easy to plot, okay? But you're going to see why I mentioned to you this is an approximation. If you plot something like that, remember, this is a cosine square, right? This is a cosine square. And we have this term here that are varying between minus pi d and plus pi d. Because sine of theta, pi d over lambda, by the way. Pi d over lambda, because sine of theta can go from -1 to +1, right? So what you're going to have here is going to be also cosine. If you plot it according to this theory, which by the way is, I mentioned to you before, is an approximate. Let's see. That should be here. It should be down, up in there. Oh, here you go. It's in the wrong place. Okay. This is the I max cosine square of that argument, complicated argument that you saw. Okay. Note that this theory predicts that the intensity of each bright spot is the same. Note that. And yet it's not what we're getting. Either way, we are getting the correct spacing between the maxima here. Okay. That's what this theory is predicting. But like I said, this theory is not telling you the whole thing, the whole story. This theory is telling you only part of the story. The theory is telling, yes, the separation between the bright spots are correct, yeah, but the intensity of each bright spot is not the same. Okay? So we're missing something in our theory. Okay? And that would be n dark equal to 0, n dark equal to 1, n dark equal to -1, and so on here. Any bright -1, 0, 1, 2, and so on. Okay, if we compare this theoretical result, right? Theoretical result with experiment, with the experimental one, we notice that this experimental, that this theoretical result states that the intensity of the bright spots n equal to 0, plus or minus 1, okay, etc. 0, 1, 2, etc. And by the way, we also have -2, -1, right? 1, 2, 3, comma, are the same. Whereas the experiments says otherwise. Okay. However, the theory still predicts the proper separation of the bright and dark spots. For this reason, this suggests that we're missing something in our theory. We are not going to discard it completely. Going to discard it completely. Okay. Because it has some predictive power. The separation, right? The separation of the bright spots and dark spots. The separation of the bright and dark spots. Further down, what is really missing in this theory? Really missing in this theory is something else that we call the phenomenon of diffraction, which we are going to model soon, which we will model soon, okay? So do not discard this result completely yet. It still has some usefulness. It's still a good result that can predict some important results. Cannot predict everyone, but it can predict some. For this reason, we are not going to completely discard, and we are going to make an adjustment to this theory later on, okay? So it is 10:35 right now. Last break was 9:26. Okay, we are going almost a little bit more than 1 hour, right? And let's see how many students we have here. 16, 15 students who arrived, attendance lecture. Okay, we must have like 2 students more who came along, right? Who are those? Let's see, Kyriakos, are you there, Kyriakos? I don't see Kyriakos. Andy, are you there? Okay, I see Andy here, but he's not answering, so I'm gonna put a star. Anybody else who is there and didn't? Daniela Galvez, I don't see it. We have 15 students, huh? Okay, good. Now we have 15. Because we have Andy that's here. Okay, so let's go for our break. It's 10:36 right now. Break. 10:36. a.m. to 10:51 a.m. Okay. So see you. Do you have any questions before we go to the break? Okay. Okay, so see you in 15 minutes. Back here. Someone here participating on their screen. Let's see. Kartika, good. Okay, good. Numbers match and let's go until 11:30, right? And then we have our half-hour break and we continue with the lab afterwards. Okay, so a reminder, right? Here are the notes. The material that's going to show up in the second exam is going to be this one. Whatever I'm covering today is not part of the second exam. And lab 1 continuation. Okay, between 12 and 2 p.m. we are going to do our continuation of the lab 1. You must have your data that you're working on that before, and then tomorrow we do lab 2. Monday, Tuesday, Wednesday, and Thursday. Chapters 33 and 34. See notes for specific sections of the chapter, of each chapter, right? Of each chapter. That's version 5 of the syllabus. Partial exams are from 12 noon to 2 p.m. The final exam is from 8 to 10 a.m. Okay. So now we're going to make a little diversion from what we have been doing, but just keep that in mind. Okay, what you see writing here does not represent completely, this model doesn't match exactly what we see in real life, but it's still very useful for the sake of this course. Later on, we are going to see how we can accommodate that change in the intensity that occurs between bright spots. There's a nice way of correcting this result here to account for what we see in real life, okay? And what we're going to do now, you already know, right? You already know that when a wave reflects off a surface, it changes phase. When, let's say, when a mechanical wave, right? Mechanical wave in a string reflect off a, let's say, reflects from its fixed end, comma, it changes phase. You already know that. The same thing, by the way, the same thing happens to light. Okay, the same thing happens to light. So in the case of your wave in the string, a wave that was upright upon incidence, comma, is reflected upside down. This is a 180 degrees phase change. The same thing happens to light. Light that's reflected from any surface is going to change its phase by 180 degrees. Okay, but wait a minute. There's more to it, right? A wave that's upright upon incidence is reflected upside down, right? But that's when it fixed, when the end is fixed, right? You already know that. We're gonna elaborate it a little bit here. There is the change. There's a phase change when a mechanical wave, the string is reflected, right? When it ends on its end is fixed. It's fixed. The phase change is 180 degrees or pi radians. It's loose, right? There is no phase change. There is no phase change. By the way, something similar, not the same thing, but something similar happens to light. Okay, something similar happens to light. But instead of fixed or loose ends, okay, the phase change depends on the reflective characteristics of a material and its refractive index. Okay. So what? You know, if light is reflected off a mirrored surface, there is a 180 degrees phase change. Okay. If light propagates towards an interface having a higher refractive index, that is 180 degrees phase change as well. You're not going to prove that, okay? You have to memorize that. There is a 180 degrees phase change as well. However, if light propagates towards an interface having a lower refractive index, that is no phase change. There is no phase change, okay? It works like that. Can you remember that? You're going to need that to solve some important problems in physics. We're going to keep track of the phase change of the light as it undergoes refraction and reflection. Okay? We are already told you that I also told you that the wavelengths of the light changes inside a medium of different refractive index, remember? Refractive index. And that there is that relationship, right? That I'm going to write it here. The wavelengths keep, wavelengths of a medium, wavelengths inside of medium of refractive index n is going to be equal to lambda divided by n. Remember that? The wavelength becomes shorter. For the sake of this course, n is always, sorry, I'm going to write it down. For the sake of this course, n is always greater than 1. Later on, you're going to learn that's not always true, okay? And that gives rise to some very interesting phenomenon. But you don't have to worry about that. It's for more advanced courses. Okay. And now with this type of information, we can start looking at interference in thin films. By the same token, that we have interference between light rays passing through a double slit, comma, we can also have interference of light waves that are reflected off thin films. And the way it goes is somewhat like that. Okay, here you go. That's a good one. Incident, here you go. This tells you everything that you need to know about interference of thin films. We have incident light, and I'm going to break it down into several slides so you don't feel overwhelmed, right? We started with everything, but okay, we start with the thin film, right? We start with the thin film. I'll call this thin film. Let's say the thin film is made of glass, and we have a monochromatic light beam propagating towards the thin film. And by the way, I gotta also put the thickness of the thin film. Here you go. Thin film made of glass, can also be made of soap, okay? But let's stick to glass for now. Made of glass, we have a thickness. And what else we have? We are going to have light, incident light, a monochromatic light beam, okay? Let's start with a monochromatic light beam. Monochromatic light beam means of a single wavelength. Incident upon this the thin film. Let's play the movie again. Thin film, glass, that's the thickness of the film. The thickness of this film must be comparable to the wavelength of the light for something like that to happen. And we have the incident light, that's the monochromatic light beam. Okay, I can even break this slide down into two, right? Here you go, incident light, and then I tell you the monochromatic light beam, the next one. So you're not overwhelmed. So we're being exposed to those illustrations over and over again, so you can memorize it more easily. In the next slide, what we are going to have, some of the light is going to be refracted. Okay? Some of the light is refracted. Some of the light is reflected as well. And when this light, let's see, this incident light, by the way, I didn't write it down. I gotta write it down right now. We have to keep track of the phases of this light to see how interference is going to affect its behavior, okay? So this incident light has a phase equal to 0 at the point just before striking the glass, okay? And then we have this refracted light. This one is supposed to go elsewhere, not here. It's supposed to come right in here, okay. And now, let's play the movie again. Make sure everything is right. Thin film, glass, thickness, incident light, monochromatic beam of light. It has a phase difference of equal to 0. And the phase should go in the next one as well. Right? And I can eliminate the refracted light for now. It's gonna come in the next slide, right? Oh, yeah. Yeah, that's okay. Am I recording, by the way? Yes, I'm recording. Good. Then we have this refracted light. Okay. We also have a reflected light beam. Okay. And when light reflects from lower refractive index to higher refractive index, it changes the phase by an amount of pi. And we have more to come. What else do we have? We have refracted light as well, right? We're doing the accounting here. And this light ray, when I put it, but it is going to refract into air. Came from air, entered the glass, and entered the air again. Okay. And then we are going to have another component here that's going to be the reflected light ray from the lower surface of the film, right? And the phase difference here is going to be 0 too, because it's going from a medium of higher refractive index to a medium of lower refractive index. Finally, we have reflected light ray 2. The reflected light ray at the lower surface is going to refract into the air. Okay, and that's what we have here. And what else is going to happen? Okay, those two light rays, you know, I spaced them out, right? In reality, there's no spacing here. All this, everything that's happening here is happening at the same spot. Because it's happening at the same spot, this light ray here is going to interfere with this light ray right here. And we want to know what is the phase difference between those two light rays. That's how it goes. Okay, I have air here, air here. Let's play the movie again. We have the glass surface, a thin film made of glass with a thickness D, incident light ray from air. This incident light is a monochromatic beam, means has a single wavelength, a single frequency, and initially this incident light beam has a phase equal to 0, your reference phase. Then there will be some refracted light ray into the thin film. But there will also be a reflected light ray. Upon reflection from a higher refractive index surface, the phase difference is going to be 180 degrees. And the refracted light ray inside the glass is going to refract into the air. But wait a minute, that is also a reflected light ray at the lower surface of the thin film, which is going to be transmitted into the air. There's no change in phase at this reflection because the light ray is incident at an interface with across which we have a lower refractive index. Okay? So now we can erase this one here. So the question is, what's going to be the phase difference between those two light rays? What is the phase difference between those two light rays? Okay. Okay, so we already know that. Here you go. I'll call this one here light ray 1, reflected light ray 1. And I'm going to call it phase 1. Okay. Phase 1 is the phase of the reflected light ray. Now let's see here. Find the phase difference between the two light rays reflected from the front. Find the phase difference between light rays reflected from two different reflecting surfaces of a thin film. So we have our first light ray that has a phase shift. Phase shift 1. I'll call that phase shift 1. And that's 180 degrees. And now we have to worry about the phase shift of the second light ray. Okay. And then the second light ray has a phase shift of phi, right? Phi 2. I should not know exactly what the phase shifts because I didn't calculate it yet. But I do know these two light rays will interfere constructively whenever phi 2, phi 1, or phi 2 minus phi 1, or phi 1 minus phi 2, phi 2 minus phi 1 is equal to a full wavelength or a full path length equal to a wavelength, or a phase angle difference equal to 2 pi m, m equal to 0, 1, 2, 3, and so on. 0, 1, 2, 3. Okay. Let's not forget, right, that phi 1 is equal to pi and consequently we end up with a phi so if the phase of 2 is 2m plus 1, oh, no, I forgot, I should put 2n plus 1 pi, then we have constructive interference, right? Let's see if it is or not. Now, let's not forget that we still have to calculate what phi 2 is and see if you end up with that or not. Okay. What we're asking here, what's the condition, right? What must be for two different reflecting surface of a thin film? I should put here of refractive index n, okay? Given of a monochromatic light of wavelengths lambda. Symbol like that. Okay. Find the phase difference. Not find the phase difference. Find it's a different problem. We need to see here. Yeah, find the phase difference for constructive. Find the phase difference between light rays. Yeah, let's leave this way. Yeah, for constructive interference, we have that. And now we're going to calculate phi 2. And let's see if phi 2 is going to be something like that. And what would be the condition for constructive interference, okay? So phi 2 is a little bit more difficult to calculate, okay? It's a little bit more difficult to calculate. How do we do that? Remember that we have a wavelength there inside. I have a wave inside here, this film, right? So this wave is going to propagate one direction and it's going to propagate another direction. Because the refractive index is different, we have to count how many wavelengths we are going to end up having in there. Okay. So the way we do it, there's a very easy way. Don't forget the path length is going to be 2d, d plus d, right? D plus d. So how do we do? You have a, we do know that a full wavelength inside the thin film, and I'm going to call that lambda prime of wavelength lambda, is going to be related to a phase angle of 2 pi. Okay. And then we are going to figure out what's going to be the phase shift whenever this light ray propagates a distance 2d. Remember, there is no change in the phase of the wave once there is a reflection at the bottom of the thin film, right? And here I'm going to put my phi 2 phase. That's how you end up finding this value here, phi 2, that I'm going to emphasize as being in boldface. Okay? A full wavelength, but it is not the wavelength in air. It's going to be the wavelength in the material. Instead of lambda prime, let me put it lambda sub n, right? Oh, let me put that lambda sub n. Lambda sub n, here you go. But we also know that this lambda sub n is going to be the wavelength in vacuum divided by n, right? And we want to find this phase shift of 2. And I'm going to solve for phi 2 on the other side. lambda sub n on the other side and 2d on the other side as well. Like that. 4 pi d. 4 pi d o times n. And I'm going to in order to have constructive interference. We must, the following condition must be satisfied. The following condition must be satisfied. Right? Here we go. We're gonna use this one again. Substitute this value right here. I'm going to pass, I already did that, right? But let's do that again. The pi to the other side. See if I'm forgetting something here. 4 pi, yeah, okay. And I will put the pi in evidence. I gotta pass the lambda as well. Let me pass the lambda first. And I gotta put the one. Take this positive sign from here. The pi doesn't need to be here, right? Let's see, two. Okay, it's 2m plus 1. 2m plus 1. 1 plus 1. Pi is here. I'm going to pass the lambda to the other side as well. Oh, by the way, that's no, before passing the lambda, I'm going to cancel out the pi here. Let's see if I didn't. Let's review what we did so far. Let's go lambda over n2d to pi 2, right? That's the condition for phi 2. That's 4 pi d n over lambda. 4 pi d n over lambda, okay? And let's see, that's the condition, right? Let's continue here. I'm gonna pass this lambda to the other side. For the n. By n. And Yeah. What else can I do here? Yeah, let's leave this way. Yeah. So that's the condition for constructive interference, right? Can we do better than that? Let's see. We can do better than that. Let's pass to the other side, 2 here, and a 2 here as well. And then we can have this condition here, m plus half. So if the round, if what you see right in here is called the optical path length of the material, okay? That twice the thickness times n. The optical path lengths depend on the refractive index, not just the distance that the light travels. Okay. So if this condition is satisfied, or even better, if I go ahead and say, look, if the thickness of your material is given by that with m equal to integer, then you have constructive interference. Okay, and then we can repeat that for destructive interference as well. Okay. Let's do that for destructive interference. You know, interfere destructively whenever you interfere destructively whenever, you know, we have 2m or 2m plus 1 pi. Whenever you have you know, pi 3 pi, right? 5 pi, etc. And then we can here write that as being 2m plus 1 pi. M equal to 0, 1, 2, 3, and so on. Okay. 2m plus 1 goes here. Then 2m plus 1 is replaced here. And what we get? We get 2. This pi sums with the other pi. This pi here sums with this other pi here, right? And 2m plus 1 pi. So that must be the phi 2 to have destructive interference. Now let's take a look at what must be the thickness of the material for destructive interference. 1135, huh? Let's finish this one before we go to our break. And we go, this one doesn't change, right? This one doesn't change because no matter what D is, phi 2 is gonna be something like that. And then, okay, I'm gonna use this relation. I didn't have to repeat this one, right? I didn't have to repeat this one because I already got what phi 2 was supposed to be to have destructive interference right here. Destructive interference, 4 pi over dn. Yeah, that's the only thing that changes, gonna be this one. And now let's finish the equation here, the derivation. Pi cancels this pi, 2 cancels this 4, pi cancels this pi, 2 cancels this 4, and 2dn is going to be equal to that for destructive interference. Oh, goodness. I gotta type it. Okay, so constructive interference. Interference condition. Constructive for a thin film. For a thin film, constructive interference is equal to that, and destructive interference equal to that. Okay, so let's see, what 1140. Any questions? We can do some numerical examples too. Let's see, 1140 right now. Okay, let's do this example before we go in the break. Okay, example. Thin film, refractive index, thin film. I'm gonna do that very quickly. N equal to 1.5, that's gonna be a glass, right? A slide of glass, a glass slide. What must be its thickness to get constructive interference of a light beam? And by the way, light beam, all of that was done for normal incidence, okay? Normally, incident over the surface of wavelengths 630 nanometers, okay? Use, find the thickness, find the minimum thickness, which would correspond to thickness, which correspond to m equal to 0. Okay. So we use this relation here. We end up with lambda. M equal to 0, we get only lambda over 2 on the right side. Okay, and the thickness and top B, D is going to be 4 for N. And the wavelength is going to be what? Again, see wavelength 630 nano. Notice that the thickness must be smaller than that of the wavelengths. Okay, if you do the math, 630 nanometers must be divided by 4 times 1.5, must be divided by 6. Okay, when we do this math, hey, wait a minute. 2d n lambda over 2 constructive interference 630. Okay, so should be around 100 nanometers, right? Approximately 100 nanometers. 105. That's how thin the glass must be to come up with a constructive interference. Okay, now 11:41 right now. And let's go for our break again. At this time, it's going to be a half-hour break. Any questions? 30 minutes break. And should be 11:45 a.m. to 12:15 p.m. Yeah, let's see. There's a chat message here. Is it 1:05? Yeah, that's right. I just approximated, right? Yeah, 1:05. I was a little bit lazy to get that 5% difference only. Yeah, a little bit more. 630 divided by 6. Okay, so I see you in half an hour. I'm back here. Let's catch up where we were doing, what we were doing last time, right? Let's see, where did we stop last time? Here's my lab records. Today is the 26th. Right, okay. And let's see how everybody's doing here. I'm gonna take attendance for the lab. Don't forget, you gotta be present during the lab in order to get credit for the lab report, okay? And I don't need that anymore. And well, I'm going to start closing some windows here that I don't need anymore. We're just going to continue on the lab 1. Oh, by the way, the sections that we have covered so far, take a look at the book, sections that we have covered on this chapter. Here you go, that's the book, right? We covered light as a wave, Young's interference experiment, interference and double slit intensity. Okay, so that's what we covered, which is not exactly what we get from the experiment, but it's close enough to make us feel encouraged to improve the theory. Okay, so it's rather straightforward. There is some approximations there that you folks have to know. And for some reason, yeah. And interference from thin films, I'll try to do that next time. Okay, microsome interferometer. The guy who invented this interferometer won the Nobel Prize. His name was Michelson. Okay, and it became a very important, Albert Michelson became a very important device. Even today, this guy used to work there at Mount Palomar. You can go, no, not Mount Palomar, sorry. He used to work at Mount Wilson, which is nearby Los Angeles. They even have a museum there displaying the interferometer that he used to use in the telescope. Which is really impressive, you know, what he did. And his interferometer was what paved the way to the theory of relativity that Einstein developed. Okay, But let's take a look here at the attendance. Amy, hand. Okay, you're there. Amy has a group, right? Let's. You, please, space. Good. Now, Amy is in group 1. Alex Hernandez. Let's see, why is that? Yeah, okay, Andy. Oh, strange. Okay, I don't know what happened here, Andy. You're not, let me see, where's the other one? Yeah, that made a mistake here for some reason, I don't know why. Let me put it back here. Right in here. Oops, no, not what I want. Search, okay, now we have it. So Andy, okay. Your group number 5, right, Andy? Okay, Alex Hernandez is in here. Okay, Emily, who? Looks like yeah, it looks like I switched Andy with Emily. Yeah, I switched Andy with Emily. Let's be here. Okay, Tartak. Thank you. Basilio, are you there?
I'm here, Professor.
Okay, thank you. Jeshwan,
I'm here, Professor.
Zaid. Oh, okay, good. Alisa,
Here.
thank you. Kartika,
I'm here.
thank you. Mary,
Here.
okay. Raymond, okay. Ashley Thai,
Here.
thank you. And Alexis
Here.
Madrigal, thank you. So we have, let's see. Oh yeah, Sydney. We still have Sydney, right?
I'm here, Professor.
Okay, and Sumana. I don't see Sumana in the list. Now, Sydney. Okay, so it looks like there's someone else here. Who was not called, by the way? Oh, Kirakos, okay. Kirakos, right in here. Nope. Okay, you do not have a group, right, Kirakos? Yeah, okay. So let me give you attendance first. And I got a 50. Yeah, okay, we're in good shape here. Let's see how are the groups here. And I have position those other students here. Oh. 15. Yeah, good. We don't need that. Now let's see how the groups are doing first. Four. Okay. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So do you know anybody here in the classroom, Kyriakos? Okay, you do not know. Okay. So, oh, okay, everybody has here every group has 3 students, right? So I'm gonna pick up, what about you join group number 5, okay? You know, exchange contact with them, and I'll put you group number 5. And you're going to need, you can get hold of them by email on Canvas. And you have to get your group folder link. Google Drive. Oh yeah, good point. Good point, Sydney. Okay, so why don't you join group 2? Kyriakos, yeah. Group 2 or group 4? Let's see. Yeah, join group 4 since they have only 2 students today, right? Join group 4. The students are Kartika, Sydney, and Sumana. Okay. Group number. Okay, so let me know if you cannot get hold of your group members, okay, Kyriakos? And you have to ask your group members a link to the group folder in my Google Drive. Okay. Okay, 15, and let's see where we stopped, right? Let's see, we were. Did you plot the graph, by the way, last time? Oh, graph 1, yeah. Yeah, we had 3 graphs to plot, right? Yeah, okay, now I'm catching up with that. Excel, let's see, graph 1. There are 3 graphs. Let's go get here, my lab 1. So everybody must open their spreadsheet, and let's also go to the notes of the last lab, right? I have everything in there. Let's scroll it down. It went Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Monday. Should have been the 21st. First, June the 24th. Okay, we are here. So I'm just gonna copy and paste what we have here. Tab on continuation, right? So plot the graphs, start from 1. Okay, we start from 1. So let's go, let's see where you are right now. there are three graphs that you're supposed to plot, and T average versus L, T square average versus L, and log of T average versus log of L. Three graphs. So I want to know where you folks are right now. And Mary, how many graphs have you plotted so far? Is Mary there? Oh, all of them. Okay. Okay, that's group number 2, right? All graphs. Okay. And Raymond, you also plot all graphs. Let me check with the other groups. Basilio, did you plot all 3 graphs?
I'm plotting the last one right now, actually.
Last one. Okay, so let's see, graphs. And plotting, yes, and working on the last one. Let's put it this way, right? Jeshuan, did you plot all the 3 graphs, Jeshuan? Hello, Jeshuan. Okay, if you don't answer me, I'm gonna put a star here in your name, okay? In case you're away from your computer, you should be interacting with the instructor during the lab. And Zaid, did you plot all the 3 graphs, Zaid? Ah, okay, good. Yes, right? Kartika, did you plot all the 3 graphs? Is Kartika there? Okay, I'm gonna put a star here on Kartika. Sydney, did you plot all 3 graphs?
No, I'm still working on them right now.
Which one are you working right now?
I'm finishing up the first and second one. I got a
okay.
little behind.
Okay, so you're working on the first and the second. Okay, good. Sumana's not here, right? So, and I'm going to. Okay, I finished 2 graphs. Let's see how I'm gonna do that. I want to put this one right in here. Right, graphs. And I'm gonna put it here 3, so I know that's the next meeting. Okay, now Suman is out. Andy, you plot all the 3 graphs, Andy? Andy, wait a minute. No, sorry, I'm calling the wrong student. Yes, okay, let me just put it here. All the 3 graphs, 1, 2, 3, right? What about Kyriakos? Did you plot all the 3 graphs? Oh, Kyriakos just joined us, right? So he has to catch up. He has to catch up. I'm gonna put it here that you're working on them, okay, Kyriakos? Okay, now Alex Hernandez. All 3, good. Yes. And Alexis Valley. Alexis Madrigal Valley. Are you there, Alexis?
Yeah.
Did you plot all the 3 graphs?
I plot the first. Let me check. I think I did. I'm pretty sure, but I had a problem with the slope value and the T squared value.
For which graph? For which graph?
For all of them. I
All of
don't.
them?
It's something I can figure out, but I just gotta take some time to figure that out.
Okay, try to figure out in the next few minutes, and I'll call the other students, and then if you have any problems, you get back to me, okay? Let me inquire with the other students here. Aimee, did you plot all 3 graphs?
Yeah, my group plotted all of them.
1, 2, 3. Okay, good. Alisa, okay, the whole group plot 3, right? Just let me know that you are there, Alisa.
Yeah.
Okay, good. Thank you. And Ashley?
Yeah.
Okay, all 3 graphs, right? And then we have Sartak. Are you there, Sartak? Oh, okay. You plot out the three graphs, right? From what I got from. Okay, good. 1, 2, 3, 1, 2, 3. Good. So the next step, I think we stopped at the significant digits, right?
Hello, Professor.
Yeah, who is that?
Jeshu.
Yeah.
I plotted two, and I'm working on the last one.
Which one did you? Okay, you were working on the last one. Okay, good. Here you go. I see. Okay, and Karsika, are you there? I give opportunity for Karsika. Okay, so let's talk about the significant digits, right? The units are straightforward, right? All you gotta do, use the main SI units and their combination. Going back here to the table. In this case, I'm putting the units here at the bottom. Sometimes I put here at the top. Okay. L is the length of the pendulum, right? The simple pendulum. T1, T2, T3 are measurements of 10 oscillations. So you gotta have the unit of time here. T average is the average of those three measurements. All those 1, 2, 3 are measurements plus L. They're all measurements. And this one is no longer a measurement. This is a result that you're obtaining from 1, 2, 3. T average is no measurement either. It's a result that you get from average, right? From the T average, and so on, right? Those are all results. They're not hard data, they're not raw data. For the case of the log of L and log T average, they shouldn't have any units. So whenever a quantity doesn't have any units, you write down just the number 1, okay? That's what units come from, right? Unit 1. So that's what you have to do. Not just here, but here we already have. Some of the places you already have the unit. All about here, I want you to look closely at the coefficient and figure out what's going to be the unit of the coefficient. The slope you're going to plot is the unit of the rise divided by the unit of the run, right? This delta that you see here is the percentage difference. Notice that I didn't put any percentage here in this cell. So you have to report the unit of percentage, which is what? Just the percentage sign, okay? And units, let's see, units go here. You gotta look closely at the table to see how I organize the table, right? Some of the tables, the units are in the vertical, and this table here, the units are in the horizontal. It's just more convenient for me to put the units in the horizontal. So watch out for that. Okay. Now, when it comes to the significant digits, I do a little bit significant figures. I do a little bit different. It's not much different, right? But I do it slightly different. I do that the conservative way, okay? And I want you to do the same in the same way, okay? Significant digits, I report them in a conservative fashion. I report only the resolution of the instrument that I use to make the measurement, okay? Don't forget, there are significant figures for measurements, and then there are significant figures for results, okay? So let's cover what the significant figures of the measurement is all about, okay? So you're making the following measurements. One, you're measuring length, and then you're measuring period of time, right? Going back here to our table. You're measuring lengths and you're measuring period of time. The number of the significant figure is going to depend on the instrument that you use, okay? In both cases, the number of sig figs of your measurement will depend on the instrument that you're using. On the instrument you're using to make the measurement. In the case of length, what we use to measure the lengths, we used a meter stick. Okay, and the meter stick has a resolution of 0.001 meters, 1 millimeter, right? Which is 1 millimeter. I'll put it the other line. Because of that, you're going to report only up to the 3rd decimal place of your measurement. Okay, you go here in your table. Every measurement that you have here must be reported only up to the 3rd decimal place, okay? So I'm gonna do just this one here, and you do the rest. Right click, format cell, right? You are not going to keep it in scientific format, you're gonna keep it in numeric format. And then you're going to adjust the decimal places. The number of decimal places is not necessarily the number of significant digits, right? So here you go, I'm gonna put 3 significant digits here, 1, 2, 3. Everything else must have 3 decimal places as well. That's the right way of reporting your measurement. Okay, you do not add more than that. You do not subtract any of those sig figs either, because your instrument can make a measurement up to a millimeter. Okay, gotta do the same for everything else here. Let me undo. Okay. So for the case of time, you know, most cell phones have my group is confused for the units of the graph 2. We aren't sure if the units should be set. But which unit are you referring to, Sartak? Are you referring to the units of the coefficient? Are you referring? Okay, you're referring to the unit of the coefficient, right? Yeah. Okay, so let's go the second graph. Let's go the second graph, right? I'll do that together with you, with everybody else. Second graph is what? T square versus L, right? T square versus L, right? Yeah, okay, so let's plot T square and L. So you're referring to the units of the slope, right, Sartak? That's what you are asking. That's what you're asking. Not the unit of the graph, but the unit of the slope, right? Or the unit of the axis. I do not know what. Remember, there are more than one unit there, right? But let's plot it. Chart out the units of the axis. Okay, good. Okay, so you're getting a straight line, right? What goes on the vertical direction is going to be T square, right? What goes in the vertical direction is T square, right? So yeah, the unit on the vertical axis is going to be second square because you're squaring T. Okay. So when you put your chart design, chart element, let's see, I'm gonna put here axis, primary vertical, right? Primary. Oh, what happened here? Something went wrong here. Let's try it again. Okay, add chart element, axis title, primary vertical. Okay, here you go. So you go ahead, you spell out the, the quantity, which is T average, with a square value, superscript square. I'm going to superscript the square. Oh. Superscript. There's a way to superscript here. Font. Okay, superscript. Okay, and then I have to subscript the average. 2, 3. Font. Subscript. But it's too small for me, right? So let's and 10 font is too small. So let's increase the size. 16, I think, is a good one. And I like the boldface. Okay, so that's what I'm getting. Oh, and I forgot. What did I forgot? I forgot the unit, right? Okay, let's put the unit here. Open parentheses. The unit is going to be second square because I squared the t average. Okay. Put the unit in parentheses. And I gotta fix this font here. Okay, now I have it right. Still too small for me to see it. Let's see if I can expand a little bit more. Yeah, too small. We gotta increase the size to make it look nicer. You can italicize it, right? That was going to be the unit for the average square. And then you're going to have the unit for L. Axis title, primary horizontal. You put L here between parentheses, always meter, right? And we're going to increase the font size. Font here. What did I put there? 20. And I got that's not 20, is it? Latin regular, let's put boldface. Yeah. Make sense now? Like that? Okay, so the units of the slope is going to be unit of the rise divided by the units of the run. Right? Yeah. Make sure you abbreviate like a second as S, not a sec. Okay? Make sure you abbreviate that as S. Otherwise, my computer may say that you put the wrong unit there. And then you gotta put the, the axis there. I'm gonna erase it. And going back to the units. The units, no, the sig figs, right? Going back to the sig figs here. Okay, so for the length, we use the meter stick. In the case of the length, we use the meter stick. In the case of time, we use our cell phone. The cell phone, we use our cell phone, the students, right? Our cell phone, which have a resolution of 0.01 seconds. That's the resolution of the timekeeping device that the students used. With this resolution, now you can display the proper number of significant digits as well of all those numbers, right? So what do? You go to format, put it number and 2 decimal places. Okay? That's how you do it. That's the right way of displaying the right number of significant digits. And when you go to the t average, you're going to have a result that depends on the sum of those 3 and a division by 3, right? That's right. Makes sense? And then you have to apply the rule of summation to get the right number of significant digits. Have to apply the rule of summation. When you sum all those 3 measurements, you're going to end up with a value that's going to have 4 significant digits, because this number here is going to go to 21.2 decimal places. Okay, so your t average is going to have 4 significant figures. Okay, let's do that. It's not going to be 3 decimal places, right? It's going to be It's not going to be 2 decimal places. It's going to be 3, because you gained a significant figure when you summed all those 3 values. Okay? See the difference? Here is one measurement, a raw measurement. Here is a result. The result ends up having more significant figures because you have to make a summation of those 3 measurements. When you make a summation of the 3 measurements in this specific case, you gain 1 significant figures, because this summation is going to be, 20 something 0.2 decimal places. When you divide by 3, you're going to have 4 significant figures divided by an integer number. So you end up with more significant figures here. When you take the average period of oscillation, right? You're going to divide this one by 10, because you time 10 oscillations. You're going to end up with 4 significant figures as well, and this one's going to be 4 significant figures. Okay, so that's the next step that you have to take. Finding the significant figures, and you do for everything. Whatever is in red, you do not need to display the number of significant digits. Every quantity in red does not require significant figures. Once you plot your graph, first graph, you're going to put the coefficient here, and you're going to compare with the theoretical result. Don't forget to put the units. Here, the coefficient, the slope, right? And then the third graph, you're going to have 2 values, 2 experimental values, one for the slope, the other for the intercept. The experimental slope is going to have a unit. The theoretical slope is going to have a unit, and the percentage difference is going to have a unit as well. So that's the step that you have to take. Here you go. Sig figs. Okay, sequence figures. So what's going to be the next one? So the order is the following, right? First, plot the graphs. Second, fill up the tables with the slope and other slope, coefficient, and intercept, right? That's the second step. Third step, work on the units, work on the sig figs, and finally, determine the CL, the confidence level, intercept. Determine the coefficient, the CL, confidence level. Do that in this order, okay? The graphs are the most important ones, because you want to make sure that you're getting what you're supposed to get. Okay, so Ashley, right? Which group are you, Ashley?
I think we're group 1.
Let's see. Group 5, you said? No. Ashley. I can't hear you. Sorry. Let me search here, Ashley. Okay, you're group 1. There you go. Group 1. Okay, let's see what's the problem with your graph, right? Group 1, right here. So let's plot. Yeah, I will. We have plenty of time here, right? We have until 2 o'clock to do that. So here you go. The first graph that you want to plot, Ashley, is T average, right? And L, right?
Yeah, we have
Okay.
those.
Were you able to highlight those 2 rows, those 2 columns here?
Yeah. So for our R-squared, we got like 0.995, and that's not something on the confidence chart.
Okay, let's do that together, right? I want to know. Here you go. So you plot the graphs, right? Here you go.
Yeah,
You plot this graph, you got something like that. And then what did you do? What else did you do? You determine the trend line, and the trend line that you used was what? The power trend line, right?
yeah,
Okay, so display equation on chart, display R square on chart. Right? That's the R square value. And that's the coefficient. Did you type the coefficient there in the table? 1826. Did you do that? 1.826.
yeah.
Okay,
So
so you got 9% difference, right? Now let's take a look at the R square, right? The R square, you need the R square and the number of data points. You have 8 data points, so you go ahead and write 8 here, and you write 0.995, 0.9995, right? Is that what you got? Oh, R square goes here. Right?
Yeah, that's what we got.
Okay, and the equation, you just copy and paste here. And hit, oops, it didn't like it for some reason. Let's try it again. Copy, 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 copy. Ah, it doesn't copy it. Ah, interesting. Okay, let's see if it copied or not. Yeah, it copied. Good. You replace the X with T, right? And then since this one is raised to the power, so you gotta format cells, superscript. Yeah, you need to go up superscript. Yes, you went superscript. Okay, so now you want to find the limits of the cell, right? That's where you're stuck. Is that right?
Yeah,
Okay, so let's get that. Let's get the table. The table is. Do you have this confidence level table? You have, right?
yes,
Okay. Now let's take a look at 8 data points, right? 8 data points here. And your R squared is what? 0.999, right?
yes,
Okay, so it's more than this value, right? So 0.999 would be here outside my table. My table doesn't go that far. Make sense? Okay.
okay,
So what do you do, right? When you have a situation like that, what do you do? Okay. All you can say under those circumstances is that your CL is going to be greater than this value and less than the limiting value of CL, which is 1. Okay? That's all you can say.
okay, thank you.
Okay? So because this table extends all the way down to 1 and to the left extend all the way down to 0, right? So that's how you handle this type of extremes, right? The points that are in the stream of the table. Okay. Now, anybody else has been having any difficulties? Let me erase everything that I put it here.
I have a question, Professor.
Yeah.
So when I'm doing graph, part of the reason why I didn't finish graph 3 is because I was trying to graph log L and then log T average.
Uh-huh.
But I think it looks like it's showing up as log, like does it matter which axis each unit or each value is on? So like, for example, I have log L on my, looks like I have that on my X axis, and then I would have log T average on my Y axis.
Yeah, that's the right thing to plot, okay?
Oh,
That's
okay,
the
good. I
right one
just
to
want to make
plot.
sure.
See that regression equation here? So
Yes.
log of the average is the Y, right? And
Okay,
log
okay.
of L is going to be the X. Okay.
Perfect. Thank you.
Anybody else?
When I put in the confidence value for the minimum and I put it in the top cell, I do 1 minus 10 to the power of negative 8, but it's just it's just calculating the value automatically and it looks wrong.
Okay, so let me see. You did what? 1 minus 10 to minus 8? Is that what you did?
Yeah.
Okay, so here you go. That's how he lives. Is he live like that?
No, it calculates the value and gives me a number, which is like, I know it's not 40,000.
Okay, so
There's no way that's 40,000.
did
yeah.
you put the equal sign here?
No.
Yeah, you gotta put the equal sign there.
Gotcha.
Okay. When you put the equal sign, it's still, 1. It's still 1 because you do not have enough decimal places, right? But if you add more decimal places here, now you get the right number. Make sense?
Yep, thank you.
Okay, make sure when you are putting the CL in there, make sure you always put the equal sign on the left side. Otherwise, Excel is gonna treat this so-called number, is gonna treat it as though it is a text, not a number. Okay? When you have a summation or subtraction in Excel, and you want Excel to do the math, you have always to put an equal sign. It goes not just for summation and subtraction, but also goes for functions. Okay, sine, cosine, log, and so on. Exponential. Okay, so Sartak, right? What the Sartak? Which group are you, Sartak? 2, right? Do you have any specific question that you want to ask? That you might be that you may need some help with? Let's go there. Let's go to group number 2, right? Group number 2, lab 2. Here you go. Oh, that's the wrong one. Oh, you're still fixing the CL values. Okay. That's not group number 2. Lab number 1. Group number 2. Here you go. Okay. Okay, so do we need help with the CLs? The confidence level? Okay, we go. Oh, you got it? Okay, good. Thank you. So that's what you, let's see what's where most of you are right now. So I'm going to do that just for lab 1, okay? We're doing 2 meetings for lab 1, so you do everything in the way that I like it be done. The difference between my labs and most professors out there is the significant digits, right? I am very conservative, so I ask the students to report the significant digit up to the resolution of the instrument. And then what else do? I do this, the confidence level, right? Confidence level that I think is a very important statistical parameter that most instructors don't pay much attention to. Okay, now let's go one by one. Again, 3 graphs, let's see. And let's see, Amy, okay, what are you doing right now? You finished the graphs, right? So let's see, the next question, did you finish the units, Amy?
Yeah, we finished the units.
Okay, what about the sig figs? Did you finish the sig figs as well?
We're still working on them.
Okay, good to know. So I presume that Alyssa, are you there, Alyssa?
Yeah, I'm here.
Okay, so you're just same as Amy, right? You finished the units and you're working the sig figs, right?
Yep.
Okay, good. Now, what about Ashley? Hello, Ashley, are you there?
I'm here.
Okay.
We do sig fig and stuff.
Okay, so you're the same, you're the same point as the other students are, right?
Yeah.
Okay, good, thank you. Tartak, did you finish the units? Oh, you're done. Okay, so let's see. Sig figs. Don't forget also that there's more here, right? You know, there's the percentage difference that I forgot to put it here. Okay, don't forget to look at the percentage difference. So sig figs, after sig figs, what else do we have? Yeah, the last one is going to be the CL. Okay, so you're telling me that you're done, right? And group number 2, Mary, you're the same level. You're also done, right, Mary? Mary there? Okay, I'm going to start here at Mary. Raymond, you're done as well? Yep, okay. So what you folks have to do, you have to prepare, make sure everything is correct there in your spreadsheet, right? You have to prepare the hard copy. Do you know how to do the hard copy? So you're gonna turn in. No, okay, we are going to turn in this spreadsheet that we have worked on, and then let me give you a sample of the hard copy. Yes, you put it's just one spreadsheet per group, okay? One spreadsheet, one hard copy per group, right? So let me go there to the place where I can get you a sample. Lab reports, lab 1, hard copy. Okay, so here you go. Let's see if this one is a good one. Okay, the way I like it's spelled out there in the syllabus, right? Lab report, physics 39, laboratory 1, simple pendulum. In this case, there's a cover page. And let's see here. Lab report format. Your hard copy lab report must be typewritten in Word format. I recommend use Times New Roman size 12 or larger, and departure from the document format will affect your final grade, right? The required information must appear in the following order. A title page, okay? We have a title page there, physics 39, by justified and separated by one line. Center justified, the information should be center justified and separated by one line, right? Physics 39, laboratory number and title, just like they have. And okay, right here. Laboratory number and title, right? And then name of the students who performed the lab in alphabetical order by their family name, okay? Order in order by their family name, just like those students, right? Atif, Inwabo. Okay, so we that time I had this group, right, with two, how do you say, two twins, right? Here's one twin, right? Two brothers, 4 students, and they're all twins, right? 2 twins here and 2 twins here. Okay, one was Daniel, the other was Dave. One was Buddha, the other was Harun. That's just an interesting piece of information, right? Group number, put your group number here. And the date the experiment was performed. In this case, or used it last time, the 21st, 23, the first meeting. Keep in mind that when I correct all of that, I will be checking if you were present, right, during the activity, okay? If you are not present, you're not gonna get credit for that meeting, for that lab report meeting, okay? In the case, for instance, of Sumana, right? She's not here, but she was before. I'm gonna give 50% of the grade to her, okay? You gotta be present so you can get the grade for the lab report. Oh, what else? Okay, the next page. Prepare a table, original data, and any results. And work on the table too. What you're going to do? You're going to copy and paste what you have there in the spreadsheet. But don't forget to increase the font size so I can see it well, right? In this case, the students, what did they do? They took a picture of the data, copy and paste it here as a picture. But you can do the other way too. There are many ways, provided it's large enough for me to see, right? Don't forget all those units. So what those students did, right? Those students, they copy a picture, right? But they could also, copy the table, right? Let's get that here. Here you go. And paste right in here. If the table is too large, you have to reformat. You have to reformat the table. Okay. Probably those students had this problem. That's why they ended up taking a picture of the table with the snipping tool. Okay. Everybody knows how to use the snipping tool, right? So you have all those tables and syllabus. Graphs, yeah, graphs are important. You're gonna get the graphs, copy and paste there. The error analysis is usually our table on the percentage difference. Okay. Error analysis, not just error analysis, also the CL, right? The CL is like an error analysis. And answer 20 questions when asked. So that's what we have. Here go tables, right? Tables. Here the graph. They didn't label the axis. See that? That's room for me to take out points, axes, and units. They could have optimized the graph. They didn't optimize the graph. They could have chopped the graph right in here and chopped the graph right in here. Okay, here's the same thing, right? Chop the graph right in here. And here's the third graph. So that's how the hard copy looks like. Any questions? So we are talking, okay, so this group is done, right? Group number 2, right? Mary, are you there? I need you to reply to me, Mary.
Yes, I'm here.
Okay, thank you. So you're done too. Okay, group number 2, if you're done, you can go. Okay. Now let's go to group number 3. Group number 3, Basilio.
I'm here, Professor.
Okay, did you find it the percentage difference?
Let's see. I have a few questions actually.
Okay, what's the question?
For the the regression equation, do I just display it the same way I see it on there, or do you want me to do something so it actually calculates something for
Display where in
for your
hard copy or in
for your
the
for your chart? You know how you did T average versus L for the first graph? I was trying to fill I filled in the units, but the right there on the left in that table, right there for for that, do I just put it as I see it up there, or is it in the graph, or do I have to make sure I can calculate something?
No, you don't have to calculate anything. Are you referring to this cell here?
Correct.
Equation. Okay. So whatever equation that you get, okay,
Uh-huh.
you gotta change. You're gonna get y equal to whatever x, right?
Correct.
Okay. You replace the x with the L in this case. Okay.
Oh,
Here you replace the x with L, and this one here, you replace the x with log of L. Okay.
oh,
The
okay,
log of
okay.
L is behaving as though as it is the x.
I see.
Okay.
And
So
then
it's,
y is essentially the T average, or in that case, the log T of T average.
yeah, that's right. Here that would be T average. I didn't put AVG there, right? AVG. 1, 2.
I think on mine you put it.
I put it. Ah,
Yeah.
lucky. Okay. And here too should be AVG, right? For some reason it's not there. AVG.
Correct.
And that's
Oh,
where
actually, on this one it didn't put it.
it is. Okay, so you can put it.
Yeah.
Okay, so we go. AVG. Okay.
Yeah, got it.
And then you have to fill up all those empty cells, right?
Correct. With the coefficient, and because you only have it, I guess it's for the coefficient you're referring to in it's for in that table right there. This is coefficient of theoretical, and then the percentage difference for D1. That one is for graph 1, correct?
This one here for graph 1, yeah.
Okay.
This
And
part
then
here for graph 1, yeah.
and then the slope is relating to the graph 2, correct?
Graph 2, that's right.
Oh,
And this
okay,
is
okay.
graph 3.
Wouldn't it be the same though? The coefficient, wouldn't it be the same as the slope?
No, because it's a different graph. Here is a power. Is a power equation, right?
Uh-huh. How
Coefficient that
come?
goes
Okay, keep going, sorry.
the coefficient that goes here is going to be close to 2.0071. But don't forget, this is a power. It's a power equation. The equation that goes here is different from this equation here. So this slope is not going to be necessarily equal to this coefficient. Okay.
Okay.
It's a different equation, right? Here is t squared equal to whatever, right? Here is t equal to whatever, right?
I think my regression equation then is the error, because they both look like the same type of equation. They have different figures right there, but or different numbers or coefficients or the slope, but they look exactly this. The structure is the same, is what I'm saying. The equation.
So let's plot it. It's gonna be T average, right? And L. That's the first graph, right?
Correct.
Okay, see if you got the same thing that I got. And then click it here. Remember, okay, oh, it's not okay. Click it here, right click. In this specific case, the trend line is not gonna be linear. It's not gonna be linear. The trend line is gonna be a power trend line. Did you put a power trend line there?
Correct.
Okay. So now do you see the coefficient that I got?
You got a little bit of a different one, a little bit different coefficient than me, but
Okay.
but not by well, I guess to me not by much.
Okay.
I got 9.5 instead of 1.5.
Okay. Okay. Well,
Yeah.
you're group number 2, right?
Correct. 3.
You're group number 3. Okay, yeah. If you're group number 3, I'm looking at group number 2 here. See that?
Oh, okay. So yeah.
Okay,
So they have a different number.
yeah, it's different. The number is going to be slightly different, right? So but then when I do the linear 1t square L, right?
Mm-hmm.
Your coefficient should be different from your slope, but you're getting a different values, numeric value.
I got my coefficient there,
Uh,
and then let's see. Wouldn't that be the coefficient and the slope? Oh wait, no, let me check. Sorry, let me put it in there. I haven't even put it in yet.
yeah.
Oh well, you know what? It's not. Now I think about it, I'm like crying over spilled milk because it's like the slope and the coefficient are both close to the theoretical. So that means
Okay.
I'm in the right ballpark anyway. So
Okay, that's good. Okay, so you got everything right, huh?
correct.
Okay, so let me erase that and let's go back here. We're talking. Okay, so you are getting a very good percentage difference, right, Basilio?
Correct. Yeah, I got 0.12 and then 0.24. Is 24 too much?
0 point now. This
Okay.
anything below 5% is great. You know, anything below 10% for the sake of this course is great. You know, because
Okay.
don't you know, don't punish yourself in getting a percentage difference equal to 0. That was the mistake that I used to make when I was a student. Okay, I would
Okay.
see a number is slightly different, then and I'll try to figure out where was the what was the problem with my experiment. There was no problem. Okay, with the experiment.
Okay.
Because my result was within 10% what was expected.
Gotcha.
And I'll
Thank you.
burn myself out because thinking that there was something wrong in there when in reality there was nothing wrong there. There was nothing wrong, right? Try to
Gotcha.
find something that doesn't exist, right? You're gonna burn yourself to death. Make sense?
Mm-hmm. Thank
Okay.
you.
Okay, so did you finish the units?
I did all the units. I'm just doing, well, actually, wait a minute. Now I guess I gotta do the units I didn't do those units for those parts. I did the one on the table
Okay.
one, the data and results. I just have to do the ones for the coefficient now and the percentage difference.
Okay, so you're working on that. Did you finish the sig figs?
The sig figs, I did it only for the L. I didn't do it I did it for also the 3 times
Okay.
or the times. I didn't do it for the T average though. Did you want us to
Yeah,
do that
well,
one as well?
yeah, you have to do for everything, right? So I'll put
Okay,
here
okay.
working. And what about the CL? Did you do the CL or did you start working on the CL?
Yes, I did the CLs.
Oh, you did the CL. So I'm gonna put a
Mhm.
Y here.
Mhm.
Okay. And now is Jeshuan.
Uh,
Go. Okay.
I'm done with the percent difference in the units. I'm still working on sig figs and the confidence level.
Okay, good. So thank you.
I have
Jeshuan.
one question though.
Yeah.
So for our values for like the regression equation, is there any way we should like use sig figs because technically we don't calculate it, it just gives us a number.
Yeah, you mean for the coefficient and for the slope?
Yes, yes.
Okay, yeah, it is possible to find the significant figures for them, but it's very difficult. It
Okay.
is lots of work. That's why that's why I put them in red. See that? That's why I put them in
Oh
red.
yeah. Yes,
And,
yes.
and the same goes for the CL, okay? There are certain things that are easy to find the significant digits, but then there are other things that's very difficult, it's too much work, and so we just skip it.
Oh, okay.
Because in order to calculate this coefficient is a huge formula. Even the R squared, is a huge formula. If you're going to keep track of every significant figure while you calculate all the steps to get R squared, it's gonna take you forever to do that.
Mm,
So here we do just the simpler ones. Okay.
thank you.
Okay. Everything that's in red color, you don't have to worry about the sig figs, but everything else you do. And next is Zaid, right? Zaid. Are you there, Zaid? Okay, I can't hear from Zaid, and I'll put a star here. Once I come back to him, I will. Zaid, raise his hand. Okay, you're there. Okay, good. Did you get the percentage difference, Zaid? Okay, I'm here. I got it. Okay, good. You got the percentage difference. Did you get the units as well? Okay, good. Sig figs. Okay, and what about the CL? Okay, so make sure you work with your group members, okay, and helping them out. And once you're all done everything, you can leave. But let me know when you're leaving. Okay, so let's see, Kartika, are you there, Kartika? Okay, I'm gonna put a star here on Kartika. And Sydney, are you there?
Yes, I'm here.
Okay, did you get the percentage difference, Sydney?
So half of our group isn't answering, so we've been just working on the graphs as of right now.
Oh, you're working on the graph. Okay.
Yeah,
Okay, so did you finish the first graph?
yes.
You
We finished it, but now I'm like figuring out the percentage difference.
Okay, and but you finished all three graphs, is that right?
Yes.
1, 2, 3. Okay, and now you're working on the percentage difference, right?
Yes.
Do you know how to do that?
Sorry, 1 second. Sorry. Yeah, I know how to do that.
You know how to do that. Okay, good. So let's go. Suman is not here. Kyriakos, did you get all the three graphs, Kyriakos? Yes, okay. Did you get everything that you need, by the way? Did you get the link to the group folder and the contact information of your group members? Ah, okay, good. Okay, what about the percentage difference? Did you get the percentage difference? Yes, okay. And work with Sydney, okay. And Kira, let's see, units. Did you get the units? Yes. Sig figs. Okay, so yes, okay, good. And the CL. Ah, you got everything. Okay, so work with Sydney, okay, and work together with Sydney and help her out and check where. Let's see, Kartika, right? Check what's happening to Kartika because I don't hear anything from Kartika. Okay, so let's go to Andy. Andy, you finish all the three graphs, right? And what about the percentage difference?
Yeah, hi, Professor. I have everything but the sig figs and units left.
Okay, so
Yeah.
sig figs and okay, so you're working on the units and the sig figs. You did the
Yep.
CL, is that right?
Yep.
Okay, what about, let's go to the next one, Alex Hernandez. I don't hear from Alex. I'm gonna put a star here in his name. And next is gonna be Alexis. Oh, okay, you're working on what? In this percentage difference? Percentage difference? Yes, okay, so you finished the graphs, right? Okay, so I presume, what about the units? Are you working or you finished them? Still working on that too. Okay, so everything else you're working on now. You're working on, right?
I have the three graphs. I am working on the percent difference. I'm also working on the units, the sig figs and the CL.
Okay, so you're working on that. You are Alex, right? Or Alexis?
Oh no, that was for
Alexis.
Alexis. not Alex.
Okay, so you're working on the CL, you're working sig figs, units, and you said you're done with the percentage difference. Is that right?
No, I'm still working on it.
Or work on that too. Okay, what about the three graphs? Did you do all the three graphs?
Yeah, I have all the three graphs.
Okay. Okay, so let me see, Raymond, when I upload that to Google Drive, it's unformatted. When you open with Google Sheet. Yeah, I know this is a problem in Google Drive, but the moment that you download it, here you go, you know, the moment I download from my side and open with Excel, everything works fine. Okay, so you don't have to worry about that. Let's see there, Google Drive, right? Google Drive. Let me show you what happens. That goes for everybody, right? This is a problem, sort of a problem with Google Drive. What you see is not what you get. Group number, your group number 2, Raymond? Yeah, okay. So here you go. Okay, so when you upload your spreadsheet, make sure you just don't put all that stuff, okay? Just keep it P39 L01G2. Everything else, you can take it out. Just rename it. So here you go. Opening. Let's see what happens. Where is your graph, right? Okay, your graph is here. And then, yeah, it's very common for Excel not to show the Google Sheets not to show the R square and so on, right? But once you download, I'm gonna download it to my hard drive. See here, I'm gonna download it. Download. Here you go. After downloading and opening from inside my computer, everything goes back to normal. Okay, see that? So nothing was lost, right? Nothing was lost. Make sure you don't put sec, but just put S, okay? That's the proper abbreviation. Whatever, whatever unit, okay? Don't spell out SEC. Just put S in there in place of sec, like that. Okay, so you don't lose anything, okay? Now, don't save it. Let's go back to the top. Amy, how's your, did you get everything? Did you get the percentage difference, right? I forgot to ask you the percentage difference, Amy.
Yeah, we're just compiling it right now.
Compiling?
Yeah, with like the cover page and everything.
Okay. So you finish everything. That's what you're telling me, right?
Mm-hmm.
Okay, you're just working on the hard copy, on the Word document. Okay, same thing for Alyssa. Is that right, Alyssa?
Yeah.
Okay, what about Ashley?
Yep.
Okay. And let's go for Sartak. So did you get the percentage difference, Sartak? I forgot to ask you that, right? Yeah, you got, okay. So, okay, so you're done. Can you check our file? Yes, upload there. I will look into that. I think you had it open. You are group number 2. Oh yeah, that's right. Let's take a look. Download right in here. This one. Yeah, I know. Okay, the hard copy you can do at home. Okay. So here you go. Yeah, I see you didn't put the units here. Okay. You didn't put the units here. Like I mentioned, replace sec by S. That would be, you put the axis title. I see that. Replace also, right? Sec by S. The lab report. We only finished the Excel. Yes, it's I went through the format, right? You're asking the format? Like this one here? Raymond? When is that? Oh, yeah, good point. When is that due? We gotta, good point. I was forgetting about that. Yeah, let's make it due. And we're gonna have, that goes here. Yeah. Lab 1 is due, let's do it Thursday, okay? Lab 1 due on Thursday. That's gonna be 29. I'll give you, since it's the first report, it's gonna take a little bit longer for you to do, so I'll give you like 3 days. And I still have to correct that, okay? And I'm going to put that in the syllabus. Lab 1 do. Lab 1 do. And because of the thick nature of this course, right? We'll have to cram in lots of things very close. And then tomorrow, let's see, lab 1 simple pendulum. What's going on here? Oh no, I put in the wrong place. Supposed to be here. Lab 1 do. And tomorrow we're gonna have lab 2. We're gonna work with a different set of data. Okay, and now let's move forward. Roster. Okay, so Mary, are you there, Mary? Huh, looks like Mary left, huh? Okay, so left. 136. Let's see. Let's put that 136, and then we get back. And Raymond is she has not been helping us with the lab today, but she did Thursday. Okay, I think she might be in AFK. What AFK stands for? Off keyboard. Okay. Okay, thank you. Okay, so you got the percentage difference, right, Raymond? Okay, and is there anything else here I gotta tell you? Yeah, it looks like you got it. Yeah, you got it right. You gotta be careful here, okay? You put 10 to minus 8, see that? My table doesn't go that to 10 to minus 8, okay? So my table goes only 10 to minus 7, okay? 1 minus 10 to minus 7. So you cannot say that the CL is between 10 to minus 8 and 10 to minus whatever, okay? You cannot say that, okay? What you can say, and by the way, you also, there's one more important thing here. Did you notice? See, this one is not the minimum value, this one is the maximum value, right? So you swapped the positions, okay? This one is supposed to be upstairs, and this one here is supposed to be downstairs. Let me see if you have the same problem here. Yeah, you have the same problem here, okay? And you do have the same problem here. Yeah, okay? So you do not put 10 to minus 8, 1 minus 10 to minus 8 here, okay? Because my table doesn't give you information about what happens at 1 minus 10 to minus 8. What you do, you put the number 1. Put the number 1 at maximum, right? And 1 minus 10 to minus 7 here. That's how you do it. Okay? 1 minus 10 to minus 7 is less than 1. Okay, watch out for that. So those were the things that I saw. Let's see here. Yeah, choo. Yeah, that looks. Oh, you gotta be careful here. Okay, you gotta be careful here. Here is okay, it's correct. Here we have 3 significant digits, and here you end up with 4. Why is that? Because, okay, why is that? Because when you sum, right, 8.99, whatever, 8.99 plus, you do gain one significant digit. Okay, you stop at 2 decimal places, but you gain one significant digit. You had 3 here, you had 3 here, you had 3 here. When you sum them, you end up with 4. Okay, that's okay. Now, when you do is this one here is different. Okay, I'm gonna sum them. See that you still end with 4 significant digits. You have 4 here, 4 here, 4 here, and you still have 4 here. Okay, so you do not report the 5th significant digit, and that applies to everybody else. Okay, that applies to everybody else. And when you turn in your spreadsheet, I'm going to correct all of that stuff. I wrote a software to do that, okay, to correct everything automatically. So I don't spend too much time correcting your lab report. I spent lots of time to write the computer program to correct it automatically, right? I did spend, a pretty large amount of time, but now, that the time that I spent in the past is paying back to me with less time. Okay, and 141, we have 20 more minutes to go. 2.4%, that's good. See, this data is pretty good. 0.4%. The percentage difference is very small. This experiment is very easy to perform. It's very, we always get good result unless the students make a mistake during the procedure, okay? I have seen students that instead of counting 10 oscillations, they counted 9, they miscounted. And just by miscounting by 1 oscillation, it was enough to give a huge percentage difference, okay? And let's go one more here. Going back. Okay, percentage difference for Raymond. Basilio, Joshua. Okay, Basilio. So how's your third graph, Basilio? Did you finish it?
Yes, I have.
2, 3. Okay, good. You finished the percentage difference. What about the units? Did you finish?
I'm just literally on the last little box of, I just have to write the slope, intercept, and the
Okay.
units for those. That's it. Other than that, though, I'm almost done.
Okay, good. So, and what about sig figs? Did you finish too?
Yes,
Okay, so only the units, right?
correct.
Okay, Joshua.
I finished the third graph, but I'm not completely done with the sig figs and the confidence level.
Okay, so the sig figs are working. Okay, what about the CL?
I'm working on that too.
You work on that too. Okay, good. Zaid, it looks like you finished everything, right, Zaid? Okay, so help your group members, okay? Before you leave, you still have 15 minutes. Okay, I'm thinking, okay. Now, Kartika, I want to give opportunity for Kartika to come along. Okay. Duncan, Ashley, Ty, let's see. Which group are you, Ashley? You're group number 1, right?
Yeah.
Okay, yeah, you may leave. Okay, you may leave. And I was at Kartika, right? Are you there, Kartika? Looks like Kartika is away from the computer. Sydney is away as well. Sumana didn't come today. Let's see. Kyriakos, it looks like you finished everything, right, Kyriakos? Andy He, did you finish the units?
Yes, Professor.
Okay, what about the sig figs?
I'm almost done with it. So yeah,
Okay.
like 5 more minutes.
Okay, good. Alex Hernandez. Still working, okay. What they're working on right now? So let's see one by one, right? Sig figs. Okay, what about the percentage difference? Oh, you didn't finish percentage difference yet. Okay, are you have any problem? You need any help? Do we need any help, Alex?
I finished everything, Professor.
And who is that?
Alexis.
Alexis, okay. Okay, so you finish everything. Okay, help Alex there. Looks like he's struggling a little bit. Okay. So, okay, I'll be here. And let's wait for some of the students to come back, right? We have 15 more minutes to go. Any questions, feel free to ask any questions. Okay, right here. I have to hang out now. Okay. Let's see, Sartak. Okay, so you finish everything, right? Okay, Sartak, you may go. Okay, when is the hard copy due? Oh, everything is due on at the day of the exam. Okay, check I just shared that with you. Lab 1 due, right? This is gonna be at the 29th. Yeah, 3 days from now. Everything, spreadsheet and the hard copy. Make sure you upload both of them to your group folder. Okay, and if you're done, you can leave. We'll stay a few more minutes here. Close this one. Wait.
Agora só tô esperando a nota da Angélica.
Ah, nota da Angélica. Quando ela disse que é preparada.
Eu já cobrei para ver se ela já emitiu.
A nota. Bom, pode já
Não,
finalizar do seu lado, né? Porque o preço não vai mudar, né?
Falta, muda o nome do fornecedor, muda o número da nota, muda os dados do fornecedor.
Deixa eu